let's start with our first topic, that is electric charges and fields. Okay, so basically electric charges. Now, before we start with electric charges, let's talk a little bit about our atom. Okay, we have already discussed about atom in class 11, second chapter chemistry. Okay, and we will discuss about that thing again in physics also in the second part, but right now let's focus only the structure of atom. An atom is made up of two things. One is a positively charged nuclei, and the second part is electrons. Okay, we know this nuclei contains further two more things, protons and neutrons. We'll not talk about that thing. We'll right now focus on electrons. So if we have an atom, this atom is made up of nucleus and the electrons are revolving around this in a particular orbit around it, right? Now what is important here is these electrons are itself having a charge, and this charge is our negative charge. Okay, negative charge. Now, how will you define a charge, sir? A charge can be defined as an intrinsic property of a charge. Let me define the charge. So, charge can be defined, it can be defined as the intrinsic property of a given object. Okay, any given object, the intrinsic property, like mass. Unlike mass, it is also a scalar quantity. We will go into the properties of charges, but charge as a simplest definition we can talk about that it is an intrinsic property of a given object. Okay, and there are two types of charge basically. One is negatively charged and another is positive charge. Now positive charge is mostly contributed by protons. Okay, so positive charge we can say it is because of proton, but in first part textbook we will talk about positive charge means lack of electron. If you remove electrons from a particular system, okay, that system will become positively charged. Similarly, if we call a negative charge is basically excess of electrons. Excess of electrons. Okay, so if any object has a large amount of electrons, we call it as negatively charged. If we remove electrons from any system, we call it as positively charged because there are lack of electrons. Let's take it a simple example, okay, from chemistry part only. Like for example, sodium has, what is the atomic number of sodium? 11, right? Now we can write the electronic configuration as 1s2, 2s2, 2p6, right, and 3s1, right? Yeah, so here how many number of electrons are there in a sodium atom? 11. And how many protons are there inside the nucleus of a sodium atom? Sir, 11. Now if we remove the outermost electron from this 3s1, it will get into a stable state, right? So if you remove this electron from the outermost shell of sodium atom, what you left with? You left with 1s2, 2s2, 2p6, right? So one electron is already gone. But what about protons? So protons are still 11. So overall charge of sodium atom becomes positive. So we write it as Na plus. When you remove an electron, the overall charge of the sodium atom becomes positive, right? So this is called as positively charged atom. So positively charged atom doesn't mean that you are adding protons. It simply means we are removing electrons. So always remember, positive charge in the whole first part textbook, we will deal with such situations only. Like if you take a battery and there is a positively charged end and there is a negatively charged end of this battery, then positively charged means lack of electron, negatively charged means excess of electron. Okay, any doubt in this part? Now let's go into some particular properties of the charges. But before that, a very important statement which is given in class 7th also, I'm repeating again, and that statement is very important, that like charges repel each other. Very, very important. Repel each other. While unlike charges attract each other. attract each other. Very, very important property. Okay. Now the question is, what is the unit of charge? So let's write the unit of charge. We will go into dimensions later on. Right now in the first lecture, we are just focusing on the unit. So unit of a charge is simply coulombs. So Coulomb is a unit of electric charge. Okay. Very, very important. So how do you write it? We write it as capital C. Be very careful, capital C, because I'll tell you what happens if you by any chance write small c. There will be an issue later on when we write another unit. So keep in mind, capital C is the unit of charge. Okay. Let's talk about the basic properties of charge. Let's go into the properties, and very important, many times asked in exams, what are the basic properties of charges? So let me just write here, basic properties of electric charge. Okay. So let's talk about basic properties. There are different properties. The first property is additive in nature. Additive nature. Sir, what do you mean by additive nature? Additive nature simply means that the total charge on any system can be added directly. So you can say that if a system, let me write it in a formal way, if a given system contains n charges, Q1, Q2, Q3, so on till Qn, then the total charge of the system. How do you write the total charge of the system? We write the total charge of the system as Q1 plus Q2 plus Q3 plus and so on. We can directly add them. No vector addition, no resultant formula, directly addition. Because charge is a scalar quantity, we will write it in another property. Okay. So this was the first property. Let's move to the second property. So second property, let me write here. So second property is conservation of charge. Many times asked question in exams, conservation of charge. Let's understand what is conservation of charge. So though you can write it like they used to write in class 9th or 8th standard, like charges can neither be created nor destroyed, they can be transferred from one system to another system. That is another way. But since you are in 12th standard, so write it properly in a proper way. So proper way of writing conservation laws is the total charge of any isolated system always remains conserved. This is our conservation law. Now, what is the meaning of this statement? Let's talk about this. Let's say if this is a system initially, and it contains a total charge of 9 Coulomb, let's say. If you break it into, let's say, 3 pieces or 4 pieces or 10 pieces, so if you break it, I'm just assuming that I'm breaking it unevenly with 3 pieces. Here it is 1 Coulomb, here it is 4 Coulomb, let's say. Then how much charge will be left in the third piece? It will be 4 Coulomb. So total charge initial of any system will be equal to always the total charge final. Very, very important for numericals for this chapter as well as next chapter. The difficulty level will rise in the next chapter, but there it will be frequently used in case of capacitors also. Okay, that we will make use. So this is actually first lecture, but first lecture, this part will be very important for the upcoming chapters. So total charge initially for any system will be equal to the sum of all the charges finally. So here it is 1 Coulomb, 4 Coulomb, 4 Coulomb. When you add them, the total will be 9 Coulomb. Understood? Okay. So here these are the two properties of charges. We'll move to the next one. So the next property, which is very, very important, and the numericals questions will be based on that, and that is called our quantization of charge. Quantization of charge. Very important for numericals. Will be used in all the first three chapters, even later, but first three chapters frequently it will be used. Okay, this property, and very important for statement as well. So it says all free charges is always integral multiple of a basic unit of charge denoted by E. So all the charges in this universe are always an integral multiple of E. Sir, what do you mean by integral multiple? Very important statement. Integral multiple means, like if I enter a classroom, let's say I entered a classroom and I say that how many students are there in your class? Somebody said 10. That's fine. Somebody said another classroom I went, somebody said it's a 20 number of students we have in our class. Okay, fine. But I went to a third class. There a student is saying, sir, in our class we have 22.54 students. Now that's not true. Exactly. You can't have a student in pieces, right? Or in fractions. So that is very, very important. The total number of charges are always integral multiple of electrons, which means you can have always integral value of number of electrons. You can't have fractions. You can have 5 electrons, you can have 20 electrons, you can have 30 electrons, you can have 100 electrons, you can have 500 or any number you can think of, but you can't have half of an electron, you can't have a 3/4 of an electron like that. So the total electrons are always, the total charge is always Q equal to Ne, where N is the integral multiple, N is an integer, like you can have a negative that will give you the negative charge. If you can have a positive charge like -5, -4, -3 and goes to infinity, and it starts from minus infinity to plus infinity, you can have. Okay, but infinite will be not, so you will take a numerical value which will lie between a minus infinity to infinity. So n will be an integer. Sir, what about E? What is E? So E is a basic unit of electronic charge. And what is the basic unit of electric charge? The charge of an electron. What's the charge of an electron? 1.6 into 10 to the power minus 19 coulombs. Now be very careful. One electron has this charge. Charge on one electron. Charge on one electron. Charge on one electron is how much? 1.6 into 10 raised to minus 19 coulomb. That's the charge on one electron. Great. Now the question is, what is the how many? Question is, let me write first question. First question is, how many electrons? How many electrons are present in 1 coulomb of charge? Now be very careful. 1 coulomb of charge is different from 1 electron. 1 electron consists of 1.6 into 10 raised to minus electron, minus 19 coulomb. But what about 1 coulomb of charge? 1 coulomb of charge. For that, we will make use of this formula. So what's the formula? The formula says the total charge Q equal to Ne. What about Q? Sir, in the question, Q is given as 1 coulomb. And what about E? Sir, 1 E is nothing but 1.6 into 10 raised to minus 19 coulombs. What they are asking, sir, they are asking the value of N. Great. So let's do one thing. Let's use the identity and find N. N is nothing but Q by E. And Q is nothing but 1 coulomb upon E is 1.6 into 10 raised to minus 19. And that is nothing but exactly 6.25 into 10 raised to 18 electrons. Sir, do we have to remember this value? Yes. Be very careful. As a beginner, many students, they take this value 10 to the power 18 as minus 18. Don't know why, but just keep it in your subconscious mind that 10 to the power 18 will be positive because numbers can never be negative. Yeah, that way, or you can think of the 10 to the power 18 is the number of electrons. How can it be negative, right? Charge on electrons can be negative, but the number of people, number of chocolates, they can't be negative in a sense, right? So 10 to the power 18, 6.25 into 10 to the power 18 electrons are transferred when you say that 1 coulomb of charge is transferred from one end of the wire to another end. Okay, so that's a very crucial value you have to keep in mind. Clear? I'll remove this. Great. So this was one part. Let's see another part, that is our let's increase the difficulty level. Let's say the question is find the total positive charge present in 36 grams of water. 36 grams of water, you have to find the total charge, positive charge. Now be very careful. Let's see here how to solve this situation. So keep your pen down, focus on the screen and understand this problem, right? So that later you can do it on your own when I'll put some questions on the screen. So here, 36 gram of water. First of all, we don't know how many molecules of water are there in the 36 gram of water, because if you know the molecule, you can count the positive charge. Let's talk about water a little bit in terms of chemistry. H2O is the chemical formula for water. And in H2, in each hydrogen atom contributes how many electrons? One electron is there in hydrogen atom. So how many atoms are there? So 2 atoms are there. So how many electrons are contributed by H2? So 2 electrons. 2 electrons. And what about oxygen atom? So oxygen atom contains 8 electrons. Be very careful. Oxygen is single atom while hydrogen are 2. So that's why 2 electrons. So total electrons present. Total electrons present will be how much? 10 electrons in each molecule. Be very careful. Now we don't know how many molecules are there here, right? So 10 electrons. And here, if total electrons are 10 electrons, first of all, we will find the molecules. To find molecules, we need a concept of chemistry, that is number of moles. So number of moles to calculate, we should know that number of moles is mass in grams over molecular mass, right? Mass in grams over molecular mass. So, sir, is the number of moles equal to number of molecules? No, be very careful with that. That's not equal. Number of moles will have a specific number of molecules that we will see later on. So, mass in gram over here is how much? 36 given mass. And what about molecular mass? Now that you should know from chemistry. Otherwise, you can see 18. 18 grams is our molecular mass of water. So we found that for this 36 grams of water, how many 36 grams, how many are the number of moles? 2 moles. Yeah. So number of moles here is, let me just write here, number of moles is 2. Now if number of moles is 2, let's figure out our molecules. Each molecule, now be very careful, each molecule contains how many each mole contains how many molecules? Number of molecules, exactly, number of molecules in 1 mole is equals to 6.022 into 10 to the power 23. Now in 2 moles, it will be 2 into 6.022 into 10 to the power 23. So that will be the total number of molecules present in 2 moles of a given water. 36 gram of water, how many molecules are there? This number. Now each molecule contains how many electrons? Sir, each molecule contains 10 electrons. So how many protons will be there? So 10 only, 10 only, because it's neutral. When you're drinking water, it's neutral, right? Because the number of electrons are equal to number of protons, right? So number of protons, or let me write here, total number of protons present in these 2 moles will be 10 into 2 into 6.022 into 10 to the power 23, right? Now that we can solve later on. So this is the total number of proton. Is it the total positive charge? No, sir. Why? Because each proton has a particular charge. So total positively charged or positive charge will be 1.6 into 10 raised to minus 19. That's a charge of a single proton into total number of protons. That is 10 into 2 into 6.022 into 10 to the power 23, and that will be in the terms coulombs. So that is the total charge. You can multiply that and you will get the total positive charge. So sir, water 36 grams, or ideally speaking a cup of water contains this much positive charge. Yeah. So what about, sir, why we don't feel shock? Because the total positive charge is equal to the total negative charge. So overall charge of the water will be neutral, right? So this is the way we calculate the total charge. Understood? Yes, you can take a screenshot. Okay. Now, related to charges, we have one more thing, that is our charge distribution, or how the charges are transferred. Okay. So we'll just initially start with a very basic idea. Later on, we will make it a little more complex in the second chapter. But right now, we'll just focus on what happens if you take two charged objects and you touch them. Okay. So let's say if we have one object like this, okay, and this contains any charge q1, okay, initially on this object, and another metallic object or conducting object that has a charge q2 on it, okay, and if you touch them and separate them, be very careful, we are touching them, okay. So we also call it as charging by conduction. We will talk about different types of charging, okay. So right now we are talking about charging by conduction. If you are taking two charges q1 and q2, and if you are touching them, so let's say you touch them, something happens between both, and when you separate them, now when you separate them again, what happens is the total charge on the first object will become q1 plus q2 whole divided by 2, and here also q1 plus q2 whole divided by 2. So basically the charges redistribute themselves. Charges redistribute themselves, okay, and equally they redistribute. They don't keep like separate, they just keep equally. So you add both of them and you divide it by 2, or simply the charge redistribution takes place like this. Understood? Now there are different types of charging, okay, like we can charge any object using friction. So let me just write, because they are simple definitions, like you must have done this in previous 8th or 9th standard. So the different ways of charging are charging by friction. So what is charging by friction? Charging by friction simply means, charging by friction means you are taking one object and you are rubbing it on another object, so that the electrons, they simply lose, one object loses the electron, another one gains it, okay. Overall charge conservation takes place, but this happens due to friction. So this is called charging by friction, okay. Like if you take a simple scale and rub it on your hairs and it will stick the papers, that is our charging by friction. You can have another one, we call it as charging by induction. Now what is charging by induction? Induction simply means what? Simply means, like if there is a object, for example this is an object, okay, and we have a rod. Let's say this is a rod, and this rod is itself is a positively charged rod. So the charge on this is positive. What will happen? It will simply take negative, it will influence the negative charges present on the first object, okay, and it will repel the positive charge present on this. The negative charge will be attracted towards this positively charged rod, while the positive charge present on the sphere will be repelled by the rod, right? So what happens in this way, if I connect a wire from this to ground, all the negative charge will go from this to ground. So basically you can make this overall charge on the sphere as positively charged. So this is also called charging by grounding, okay. We will talk about grounding in the second chapter, you know. Yeah, that's what, attraction takes place here, but they don't stick together. This is very important about induction. In case of conduction, as you have seen here, what happens? The charges redistribute. So basically if you remove this rod, again the sphere will become neutral, because the total positive and total negative charge will be same. So the influence is only there until the rod is there. It is like you are getting scared from a strict teacher in your classroom. Once the teacher enter the classroom, everyone is silent and they're doing their work. Moment that strict teacher goes out of the classroom, everyone, they redistribute themselves as they work. So it is like if okay, so when the strict teacher is teaching, everybody is looking at the board, focusing on what he is saying. But moment the teacher goes, the students, they redistribute themselves. Understood? So question says, if a body is negatively charged, then it has excess number of electrons, because more the negatively charged, more number of electrons. Okay. So we will talk about here. The correct answer is option A, excess of electrons. Okay. Let's move to the question number 2. So the question here says quantization of charge. What does quantization of charge implies? It simply implies that the charge on an object is always integral multiple of electronic charge. That is option D. Let's move to the third one. It says number of electrons present in 1 coulomb of charge, that is 6 into 10 raised to 18, or if you are given with 6.25 into 10 raised to 18, that is also fine. Okay, so even B is correct, and if you are given with 6.25, that's also fine. So they have approximated it as 6 into 10 raised to 18. Charge on 10 kg electrons will be. So basically, first we have to find what is the mass of one electron. So mass of one electron has a mass of 9.1 into 10 to the power minus 31 kg. That's the mass of a single electron, right? So first we will have to find that how many electrons are there in 10 kg. So number of electrons in 10 kg will be equal to 10 over 9.1 into 10 to the power minus 31, right? So I'm just approximating it as 9 instead of 9.1. So if you divide 10 by 9, you will get approximately 1.11 into 10 to the power plus 31. These are the number of electrons in 10 kg. Now each electron, one electron has a charge of 1.6 into 10 raised to minus 19 coulombs, right? So total number of electrons we have how much? 1.11 into 10 raised to 31. So total charge that would be 1.6 into 10 raised to minus 19 multiplied with 1.11 into 10 raised to 31, right? Now 1.11 into 1.6, that will give you approximately 1.77 into 10 to the power now 31 minus 19, that is nothing but 12 coulomb. So approximately option A is correct, 1.75 into 10 to the power minus plus 12, sorry, coulomb. That's our correct answer. Yes, our next question. Charge is a scalar quantity or vector quantity? Charge is a scalar quantity. That's correct. So let's move to our next one. Here. So in the process of charging by induction, the correct answer is there is neither loss nor gain of electrons by the object. That's the correct answer. Let's move to the next one. The amount of negative charge present in 72 grams of water. So first of all, what we will do is we will first find the number of moles. So number of moles will be equal to how much? 72 divided by 18. So from where you got 18? 18 is the molecular mass of what? So 18 and that will give you how much? 18 fours are. So 4 moles are there in our the 72 grams of water. So number of molecules will be, let's see, number of molecules. So number of molecules will be 4 into 6.022 into 10 to the power 23. That will be our number of molecules. So if this is the number of molecule, let me just multiply this. 6.022 will be 24.088 into 10 to the power 23 molecules are there. Now each molecule of water contains how many positive charge? They are saying no, negative charge. So how many number of electrons? Number of electrons which are total present in one number of electrons in one H2O molecule. Since the hydrogen is contributing 2 electrons and oxygen is 8, so total is 10 electrons are there. Yeah, so the total electrons will be Let's multiply the molecules. Total electrons will be equals to 10 into 24.0288 into 10 to the power 23. So that simply I'll increase the power. So 24.088 into 10 to the power 24. That will be the number of electrons, and the total charge, multiplying it with the charge of an electron. So total charge will be simply multiplying it as how much you got? 1.6 into 10 raised to minus 19 into 24.24, correct? So let's multiply 24.088 into 1.6, that will be 38.54 into 10 to the power 5, and that's our coulombs. So its correct answer is option B. It should be in coulombs. That's the unit. Okay. If a metal sphere A has initially 6 coulomb charge on it, so let's draw it over here. Let's write here 6 coulomb. It is touched with another metal sphere B. Let's call it as A, and this is our B, and it has minus 2 coulombs. Okay, the final charge on both the spheres. So what happens? We have learned Q1 plus Q2 divided by 2. So the new charge on A will be equals to 6 minus 2 whole divided by 2, that is equals to 4 by 2, which is 2 coulomb. Yeah, and whatever charge is on A, the same charge will be residing on B. Yeah, so that will be also 2 coulomb. So correct answer is option B. So the correct answer for this is like charges repel each other. That's correct. Let's move to the next one. So the question says, in the process of charging by conduction, the final charge on the object is negative. Then the mass of the object is, see, first thing is the final charge, okay, is negative. Something is negative. What it means, we have learnt in first lecture. If something is negative, it simply means we have added the electrons, right? So if you are adding electron, its mass will be slightly increased, slightly. So correct answer is option A. It will slightly increase. Yeah. Oh, I think that's a misprint. Is a coulomb of charge is greater or the charge of an electron? Or it should be. Yeah, so it's a coulomb of charges which is greater than the charge of electron. 1 coulomb of charge is having 6 into 10 raised to 18 electron. That's correct. So the question over here says, the amount of negative charge present in 63 gram of HNO3. So first of all, let's find the molecular mass of HNO3. So HNO3 molecular mass, hydrogen is 1, nitrogen is how much? 28 or 14 it is, I think. 14, and oxygen is 16 3s are 48. So that will be our 49 plus 14, that is equals to 63, right? So if HNO3 is 63, molecular mass is 63 gram, let's calculate first the number of moles. So the number of moles present in this will be equals to 63 over 63. That's equal to 1 mole, correct? So if number of moles is 1 mole, number of molecules, let's figure out. So number of molecules will be equals to our 6.022 into 10 to the power 23. So in 1 mole, this much amount of molecules are there. Now each HNO3 atom or molecule, that is how many number of negative charge is present? In each HNO3, it will be electrons is HNO3, 1 hydrogen atom, 7 nitrogen, and oxygen, there are 3 atoms. So each oxygen atom 8 3s are 24. So that will be 20. Yes. So 25 plus 7, that is equals to 32 electrons in 1 atom or 1 molecule, basically. Not 1 atom, 1 molecule. So for 1 molecule of HNO3, there are 32 electrons, because we are looking for negative charge. So if there are 32 electrons, the total electrons in this will be, total number of electrons will be equals to 32 into 6.022 into 10 to the power 23. Okay, so this will be our let's move this part, 23. Yeah, so the total charge will be total negative charge, that would be 32 into 1.6 into 10 raised to minus 19 into 6.022 into 10 to the power 23, right? So let's simplify and solve it. 32 into 1.6 into 6.022. So that will give us 308.3 into 10 to the power 19 and 23. That will be how much? Minus 19. That's 4. So the correct answer will be option C, 3.08 into 10 to the power 6. Any doubt? Do the next one. Let's see. Question says the charge carried by 25 into 10 to the power 10 electron is. So let's first find, let's use the very basic formula, Q equals to NE. And N is nothing but here given as 25 into 10 to the power 10 into E is 1.6 into 10 to the power minus 19. So let's multiply 25 into 1.6, that would be 40 into 10 to the power minus 9 Coulomb. That's option B, correct. Do the next one. If a metal sphere has initial charge Q on it, is touched to, okay, so there is a metal sphere, initial charge is Q on it, touched to another metal sphere, let's call this as sphere A, and there is another sphere B which has 3Q charge on it. The final charge on each sphere after they are removed from contact, yeah, so their charges will redistribute. So the final charge on A will be Q plus 3Q by 2, and here also it will be Q plus 3Q by 2. That will be how much? 4Q by 2, which is 2Q. The correct answer is option B. Do the next one. A metal sphere A has initial charge. So let's draw a diagram over here. This is our A, has a charge Q on it, okay, is touched to another metal sphere B. There is another metal sphere B having no charge initially. B has no charge initially, so charge will be 0 here. Now the metal sphere B is touched to a third metallic sphere C which has a charge 3Q on it. So let's write here C, and this is our 3Q. Now when B is touching C, the charges will redistribute. So the new charge on B will be 0 plus 3Q over 2. So that will be 3Q, 3 by 2Q. And the final charge on B. So this will be our final charge. Wait, let me just read it again. A metal sphere A has initial charge Q. Oh, okay, wait. We have done a very small mistake over here. So this is our ABC. Now the question says, it is touched with A is touched with B. So when you are touching A and B, the new charge on A will be Q plus 0 over 2, and B will be also Q plus 0 over 2. So new charge on B after touching with A will be Q by 2. So if Q by 2 is the new charge on B, now you are touching it to C. So if you are touching this to C now, this is our B dash. Now it's already having a new charge. Now you are touching it to C. So that will be 3Q. Now this on touching will give us Q by 2 plus 3Q whole divided by 2. And that will be how much? 7Q by 2 whole divided by 2. So that is 7Q by 4. So the correct answer over here is option B. Understood? We'll move to the next one. If a metallic sphere A has an initial charge of Q on it, okay, is touched to another metallic sphere B having no charge initially. So if B has no charge, I am putting here 0. Okay, now if they are touching, the A will have a final charge as Q by 2, Q plus 0 by 2, and B will also have a new charge of Q by 2. Now the metal sphere B is touching the metal sphere C which has initial charge of 3Q. But they are saying what is the final charge on A? So final charge will be Q by 2 only because it is not affected by at the last. So option C is the correct answer. Understood? Let's move to the next one. A metallic sphere A has a charge of 10 Coulomb. So let's draw it over here. This is 10 Coulomb over here. It is touched with another sphere B having a charge of minus 4 Coulomb. So let's write here 4 Coulomb minus, and that's B. If you are touching it, A will have a new charge of 10 minus 4 whole divided by 2, and that's equal to 3 Coulomb. New charge on B will be equals to again 3 Coulomb because it will be redistributed. Now the metallic sphere B is touched with this third sphere C. Now that's a C with the 7 Coulomb of charge. Final charge on C you are asked. So when you are touching B and C now, the B is already having 3 Coulomb this time, not minus 4. So 3 and 7. So C will have a new charge of 3 plus 7 Coulomb whole divided by 2, and that is equals to 5 Coulomb. That's correct answer is option A. Understood? Now we'll move to the next one. A metallic sphere A has one second, let's go back. Okay. So question says a metallic sphere A has 10 Coulomb of charge. Touched with another metallic sphere B with minus 4 Coulomb. So the new charge on A is nothing but 10 minus 4 over 2, that is equals to 3 Coulomb. And new charge on B is also 3 Coulomb. Now the metallic sphere is touched with C having a charge of 7 Coulomb. Find the final charge. Now A is not affected, so the final charge on A will be 3 Coulomb. That's option C. So the question says how many electrons would have to be removed. You have to find the n value so that it leaves a positive charge. So let me just again use the formula Q equal to NE. N we have to find, so N will be Q by E. And we know that 1 by E is nothing but 6.25 or approximately 6 we will use, because the options are in terms of 6. 10 raised to 18 electrons, right? So Coulomb charge is given as 10 to the power minus 9 Coulomb over, that will be multiplied here. So into 6 into 10 raised to 18. Okay, so that will give us approximately 6 into 10 raised to 9. And 6 into 10 raised to 9, that can be written as 0.6 into 10 raised to 10. And that will be option B. So an alpha particle is He2 plus. Yes, He2 plus is the correct answer. Okay. So in the last lecture, we discussed this whole thing. Okay. Let's move ahead and see our next part, and that is our Coulomb's law. Let's see now Coulomb's law. Let's see our next topic, and the next topic over here is Coulomb's law. So let me write here Coulomb's law. Let me just make it. Okay, Coulomb's law. Let's see what is Coulomb's law. So Coulomb gave a particular law which gives us the magnitude of, or the amount of, along with the magnitude, the direction of force acting between any two charges. Okay. So let's see what Coulomb says. Let me write the definition, very, very important for exams. It says the force between 2 point charges, is inversely proportional to the square of the distance between the two charges, and is directly proportional to the product of the magnitude of the two charges and it acts along the line joining the two charges. So this is our Coulomb's law. So basically the idea of Coulomb's law is, if you're given with any two charges, let's say this is our charge Q1 and this is any charge Q2. These are point charges. What are point charges? They are very small in magnitude compared to the distance between them. Okay. So these are any two point charges separated by any distance r. Then according to Coulomb's law, Coulomb said that the force between them is directly proportional to the product of the two charges q1 times q2, and it is inversely proportional to the square of the distance between them. So F is inversely proportional to square of the distance between them. When you remove this proportionality sign, we know that it will give us a constant K. Q1, Q2 over R square. Be very careful. There is a magnitude over here, which means we don't take the negative sign. Sir, why we don't take the negative sign? Because it acts along the line joining the two charges. So direction, it's a vector quantity. We will see when we will solve problems that what will be the role of this magnitude in this particular expression, right? So F equals to K Q1 Q2 by R square. That is the force acting between the two charges, and it acts along the line joining. So if both of them are attractive, if, for example, if one is positive and one is negative, the nature will be attractive. Attractive means if Q1 is positive, it will be attracted towards the negative charge in this direction. And if, let's suppose, they are both of the same sign, let it be both positive, let it be both negative, they will be repelled in this direction. So that will be the direction, right? So direction we will see later on. Here, the K value, K the constant, is nothing but 1 by 4 pi epsilon naught, where epsilon naught is known as the permittivity of free space. Permittivity of free space. Now, sir, what's the idea of permittivity of free space? What do you mean by permittivity of free space? If I assume that if I take the same two charges, Q1 and Q2, and if I put them, dip it inside the water at the same separation. If I take the same two charges at the same separation and put it inside the water, will I get the same force? No. So what happens? The permittivity of that medium will be different. So permittivity of free space is nothing but 8.854 into 10 to the power minus 12. That's the value of epsilon naught. So what's the unit of epsilon naught? So that unit we can find simply by putting it as F equals to 1 by 4 pi epsilon naught Q1 Q2 over R square. And if you take everything on the left hand side, you left with epsilon, take the epsilon naught on the left hand side and take this force on the right hand side and epsilon naught on the left hand side. What will you left with? You will be left with Coulomb square over Newton meter square. Any doubt? Now, this is the unit of epsilon naught. And if I put the value of this epsilon naught in this K, if I put the value of this epsilon naught, I can see on the right hand side, everything is constant, right? 4 is constant, pi is constant, and even epsilon naught is constant. So if you put the value, you get a value, specific value of K, and that is nothing but 9 into 10 to the power 9. So that's the unit of K, not epsilon naught. Be very careful. Epsilon naught is 8.854, 10 to the power minus 12. And K value is 9 into 10 to the power 9. And it is, you can see in the relation, they are reciprocal of each other. So the units will be also reciprocal of, So this is the value of K. And that is the value of epsilon naught. Now using this, you can also find the dimensions of epsilon naught. So this is called as permittivity of free space, and that is our Coulomb's law. Coulomb's law says that you can figure out the force acting between any two charges, and these two charges, okay, will experience a force along the line joining the two charges. So what happens if you have multiple charges? That we will see in the particular questions. So the question over here says two charges, 3 nanocoulomb. So let me just put it as Q1, that is equal to 3 nano. Nano, in case if you don't know, it's 10 to the power minus 9 coulomb. Okay. And Q2 is nothing but 5 into 10 to the power minus 9 coulomb. Okay. And both are separated by 30 centimeter. Be very careful. You have to use standard units because everything is in newtons. So it should be 30 into 10 to the power minus 2 meter. Now the force acting, force will be given by Coulomb's law that says F equals to, always write the formula before you solve the question, because in board exams they will give you marks for each and everything. Given data has a different marks, formula different marks, and then you have to substitute. So 1 by 4 pi epsilon naught, 9 into 10 to the power 9. Q1 is nothing but 3 into 10 to the power minus 9. And Q2 is 5 into 10 to the power minus 9 and whole divided by R square, where R is nothing but 30 into 10 to the power minus 2 into 30 into 10 to the power minus 2. Now let's simplify it. So let me just make it as 9 into 3 into 5. I'm just keeping the numbers separately. I'm just explaining you how to approach so that it can be easy. 10 to the power 9 and 10 to the power minus 9. That can be cancelled and you left with minus 9 on the top. Let's see the denominator. Now 30 and 30. 900. 900 and 10 to the power 1 of the minus 2's goes. You're left with 9 into 10 to the power minus 2. 9 and 9 goes and you're left with 15 and 10 to the power minus 7 newtons. That's option A. Any doubt? We'll move to the next one. The Q1 is the charge on first metal sphere. So let's draw a metal sphere and it has a charge Q1, and Q2 is the charge on the second metal sphere. Okay, fine. This is our Q2. The force acting between them will be repulsive. Now, repulsive is between when it is like charges. Now, like charges means either both of them are positive or both of them are negative. So, both of them are positive. So, positive into positive will be positive and negative into negative will also be positive. So, Q1 into Q2 should be greater than 0. So, correct answer is option. Let's move to the next one. Two charges 10 microcoulomb. So let me just write here Q1, and that is equals to 10 into 10 to the power minus 6 coulomb. And the second charge Q2, that is equals to minus 5 microcoulomb, 10 to the power minus 6 coulomb, are separated by a distance r will be equals to 5 centimeter, 5 into 10 to the power minus 2. The force acting between the two charges, so we will use Coulomb's law, that is 1 by 4 pi epsilon naught Q1 Q2 whole divided by r square. So 1 by 4 pi epsilon naught, that is nothing but 9 into 10 to the power 9, and Q1 is nothing but 10 into 10 to the power minus 6 into Q2, that is minus 5. Now be very careful, you don't have to take the negative sign as per the relation because it has a magnitude over here, whole divided by 5 into 10 to the power minus 2 whole square. So I'm just separating them and writing them like this. So now we can split them. 5 cancels with 5, 5 2s are 9 2s are 18, and let's now simplify the powers. So in the numerator, it's 10 to the power 9 and minus 6 and minus 6, minus 12. So 9 minus 12 is minus 3 whole divided by 10 to the power minus 4. So minus 4 goes up, that will become 18 into 10 to the power 1, and that is nothing but 180 Newton. That's the correct answer, option B. Understood? Try this one. Okay, now keep your pen down and understand this concept. This is very, very important. Okay, this type of questions will arrive. So let's start with question. Question says, three charges Q, Q and 2Q are placed at the corners of an equilateral triangle. So let's draw an equilateral triangle. Let's say this is an equilateral triangle over here, and there are three charges. So I'm just randomly putting them Q, Q and 2Q in the order, right? Now let's call this as A, and let's call it as B, let's call it as C. Now it says of side length A. So I'm just assuming that this is our side length A. Each one is A only. Net force acting on the charge 2Q will be. So to calculate this force, first thing you have to understand that before we apply the formula, we have to first draw the directions. So if there is a charge A and C, between charge A and C, the force will be attractive or repulsive. So it will be repulsive because both are positive charge. They have not said that any one of them negative. So this will be the repulsive force acting on C due to A. Any doubt? Now force acting on C due to B, again it will be repulsive, but repulsive along which direction? Along the line joining the two charges. So it will be FCB. Any doubt? Now if this is an equilateral triangle, we know that each angle is 60 degree. So the angle between the two forces will be 60 degree over here. So whenever you have such type of problems, first you have to draw the directions and give the angle between them, right? Then you go to the magnitudes. So let's write the magnitude of force acting on C, FCA, force acting on C due to A. That will be equals to K, the charge of first one Q, the charge of second one 2Q whole divided by separation, which is A square. So I'm just rewriting it as 2KQ square by A square. Any doubt? Now force acting on C due to B will be K, the charge on the that will be Q, that will be 2Q whole divided by A square, and that will be equals to 2KQ square by A square. Now we have two vectors FCA and FCB. You can't add them directly. Be very careful. You have to use the resultant formula. That will be root under FCA square plus FCB square plus twice of FCA, FCB, cos of angle between them, that is 60 degree. Now in case if you don't know the value of cos 60, it's half. Yeah. So FCA and FCB both are equal vectors. If they are equal vectors, you can directly, instead of substituting the values, you can simplify the expression as FCA square. CB also, since it's equal to CA, I am just writing it FCA square, and 2 times FCA into FCA. This is an easy way of solving such expressions. So now you can cancel this 2 with 2. You're left with under root FCA square, FCA square, and FCA into FCA, FCA square. Now let's so these are FCA, FCA, FCA. 1 apple plus 1 apple plus 1 apple, 3 apples, so 3 FCA square. Now if you take the root, it will be root 3 FCA. Now what's the value of FCA? You can see on the top, it's K into 2 times, so it will be 2 root 3 KQ square by A square. That's option A. Understood? Do this. Question says over here, 3 charges Q, 2Q and 3Q are placed at the corners of an equilateral triangle. So let's draw again an equilateral triangle here, and that is Q here, 2Q over here and 3Q over here, and the side is A here, right? The net force acting on the charge 3Q must be, so we have to find the net force on 3Q. So first of all, 3Q and Q, that is repulsive, so it will be directed in this direction. Let's call it as A, B and C. So it is force acting on C due to A. Now force acting on C due to B will be repulsive in this direction, FCB. Angle between, since it's an equilateral triangle, 60 degree because of this angle, vertically opposite angle. Let's write the magnitude of FCA. Magnitude of FCA will be K, Q, 3Q whole divided by the separation is how much? A. So A square. So it will be 3KQ square by A square. Now what is the force acting on C due to B? It will be equals to K, 3Q, that's the charge on C. B is 2Q, so 2Q whole divided by A square. So it will be 6KQ square by A square. Now, since these are 2 vector quantities, so resultant will be root under, be very careful, this time the forces are not equal. So FCA square, FCB square and plus 2 times FCA, FCB cos of 60 degree. So here we will substitute the values FCA square. So it will be, if you square this whole thing, it will become 9 KQ square by A square. I am just keeping it as whole square. Plus FCB, which is this one. Let's square it. It will be 36 KQ square by A square whole square. Plus 2 times FCA. That's 3 into KQ square by A square. And into 6 into KQ square by A square. And into cos of 60, which is 1 by 2. Let's cancel out half with this. And what we left with? We left with, now let's write it over here. Let's take KQ square by A square common in all the terms. So KQ square by A square common. Here we left with 9. So let me just write it properly. 9. Here we left with 36. And there we left with 6 3s are 18. So out of root we can take it out, and that will be our KQ square by A square. Yeah, because whole square is there. So 36 plus 18, 9, 3s are 27, 27 and 36, that will be root 63. So is there any option? Yes, option B is correct. Three charges Q, minus Q and 2Q are placed at the corners of an equilateral triangle. So let's draw an equilateral triangle over here. Let's say this is our equilateral triangle with charges Q, minus Q and 2Q over here. And having a side length of A. So each side of this equilateral triangle is A over here. The net force acting on the charge minus Q. You have to find the charge on net force acting on minus Q. So let me just keep it here, minus Q over here. Okay, we have to calculate. So we know that if we call it as A, let's call it as B, let's call it as C. The force between A and C, that A and B, sorry, that will be attractive. So it will be along the line joining the two charges. So let me call it as FBA, force on B due to A. Force on B due to C, that will be acting in this direction. So force on B due to C, and the angle between them is 60 degree, right? So let's write here theta is 60 degree. If theta is 60 degree, then cos 60 over here, that will be nothing but half. Great. So here our resultant R, that will be equals to root under, we know that FBA square plus FBC square plus 2 times FBA BC into half. Cos 60 is half. So let's figure out what is the value of FBA and FBC. So let me just write it over here. FBA, that will be by Coulomb's law, K Q1, we will not take the negative sign, Q2, so KQ square by separation A square. Similarly, force on B due to C, that will be equals to K Q and into 2Q. So that will be 2Q square upon A square. So let's substitute these values over here. That will give us KQ square by A square whole square. FBC square, that will be 4 times KQ square by A square whole square, and plus FBA into FBC, that will be 2 times KQ square by A square whole square. Yeah. Now let's take common here. This will give us KQ square by A square whole square. Taking common, we left with 1 plus 4 plus 2. So this will give us 4 plus 2, 6 plus 1, 7. So this will be root 7 KQ square by A square. So correct answer is option C. I'll move to the next one. Two charges Q1 and Q2 are separated by a distance d. So let me just write here that let's say this is our Q1 and let's say this is our Q2, and both are separated by a distance capital D. If both Q1 and D are doubled, so even Q1 is doubled and D is doubled, the force will become how much? So let's say what is the force initially? The force F will be K Q1 Q2 whole divided by D square. Now when Q1 is doubled, the new Q1 will be Q1 dash, that will be equal to twice of Q1, and new distance, new separation D dash is twice of D. So the new force will be F dash, that will be equal to K new charge on the Q1 into Q2 is still same, whole divided by D dash whole square. Let's substitute the values. So this will be K into 2Q1 into Q2 whole divided by twice of D whole square. So that will give us here as 2 times K Q1 Q2 whole divided by 4D square. Now K Q1 Q2 over D square, that's nothing but this part over here, that is nothing but force, the previous force. So it will be 2 by 4, that is 1 by 2 of F, that is F dash. So the correct answer is, it is halved. Understood? Let's see, the next one says unit of permittivity. Unit of permittivity is our Coulomb square per Newton meter square. That's the correct answer. So this is option D. Let's move to the next one. Let's see. So question here says dimensions of epsilon naught. So first of all, the unit of time for that, let's first write Coulomb's law. F equal to 1 by 4 pi epsilon naught Q1 Q2 whole divided by R square. So epsilon naught, that will be nothing but Q1 Q2 whole divided by 4 pi epsilon naught FR square. And if we write the units for Coulomb square whole divided by Newton meter square, that will be the units. Now let's write the dimensions. So first, my mistake. Okay, so now this will be Coulomb square per Newton meter square, and here the Coulomb has a dimensions of AT, where A stands for ampere, T for time, From 10th standard, I is equals to Q by T. So Q is nothing but I into T. So current has a unit of ampere and time has seconds. So dimensions is 80. And N, Newton is M1, L1, T minus 2. Meter square, that's nothing but L square. So when you take it on the top, this will become M minus 1, L minus 3. And A is as it is, and T power plus 2. And A square, no, T is plus 3, I think minus 2 goes up, it will be minus, so it will be square over here. I have done a small mistake, yes, so it will be A square and T will be T to power 4 and this minus T square and this T to power minus 4 it will be. So minus, it will go up and it will be plus, so that will be yes. So that will be option B is the correct one, yeah. So maximum they can give you up till 4 charges, right? So question over here says 4 charges Q, Q, Q and minus Q are placed at the corners of a square. So let me just draw a square over here. Let's say this is our square and this is our Q, 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 and you have to put it in the same order. So it will be minus Q over here, right? Okay, side length of each of this is A, right? The net force acting on minus Q. Now minus Q is attracted along this direction by the first charge. So let me call it as F1. It is attracted towards the second charge. Let's call it as F2 along this direction and F3 along this direction. Correct? Now F1 and F3 both are at 90 degrees. So let's first find F1 magnitude. So F1 magnitude is nothing but K Q square by A square. Right? And F2, that will be K Q square by A square. Both are equal. F3, not F2. Yes, F3 is K Q square by A square. Now, the resultant of any two vectors which are perpendicular to each other, you can directly write it as A square plus B square. You can put it as A square plus B square plus 2AB cos theta, but theta is 90 over there. So, cos 90 is 0. So here if A square and B square both are same, then we can straight away write it as A square plus A square, and that is nothing but twice of A square, which is root 2A. So adding F1 and F3, they are both same. So resultant of F1 and F3, that will be simply R will be equal to root 2. You can write any value because both are equal, K Q square by A square. And where will be the direction? From parallelogram law of vector addition, if both are equal vectors, that will be inclined equally at 45 degree. So this is our R. Now as we can see that R and F2 are along the same direction. So we can directly add them because the theta is 0 degree between them. So F2 is nothing but K, first charge is Q, second charge is minus Q, so K Q square whole divided by the separation between this minus Q and that minus Q. Now there you need simple Pythagoras theorem. So you can write it as root 2A. That's the separation between minus Q and that plus Q. So this whole square, which will give us K Q square over 2A square. Right. So this is F2. So net force acting on minus Q charge will be F2 plus R. And F2 is nothing but K Q square by 2A square and plus K root 2 square by A. Now let's take K Q square by A square common, and we left with over here as into 1 by 2 plus root 2, and that's nothing but option A. Understood? Okay, so in the last lecture we defined Coulomb's law. Okay, now in Coulomb's law we learnt that how we find the force between the two charges. Okay, let it be positive two charges, negative two charges. Okay, and this was our Coulomb's law in the previous lecture. The force was proportional to the product of the two charges and inversely proportional to the square of the distance between them. Okay, now then we require one more concept to define force, and that concept is concept of electric field. So let me just write here electric field. Let me zoom it a little bit. Okay, so here it is electric field. Our next topic is electric field. Sir, what do you mean by electric field? Electric field is a region around any charge. So, let's say if there is a charge, positive charge, you can think of negative charge also. There is a region around this charge. Around every charge there is a region, and in this region, if you take a negative or another positive charge or any charge inside this region, it will experience a force. If you keep it outside this region, there will be no force. I think you must have done this with the magnets also. If you take a magnet and this is another magnet, north attracts south, but up till a region. Like if you keep the magnet in one room, another magnet in any other room, not necessarily they will attract depending on their field. But if you keep them close by, they will attract, right? So, electric field is a necessity to define force. It is a necessity to define Coulomb's force. So, let's define electric field. What is electric field? It can be defined as the force that a unit positive charge would experience if placed at that point. Which means if you place a small positive charge at any point in the region of the source charge, we call this charge as source charge whose electric field we are looking for. If you place this small test charge in the region around this positive charge, it will experience a force. Sir, why you are talking about this test charge being small? This should be small so that it should not affect the field or the position of the source charge. If by any chance, if I place this small q over here, it should not change the position of the source charge. Okay. So, positive charge plus q, the field at any point r distance away. So, let me just draw it over, not here. Let me just draw it that side, this small q. So, that let's say we are placing it over here. And this is our source charge, and let's say this is the region, this is the point at which we are finding the electric field. So, according to Coulomb's law, the force acting between both will be equals to K Q over R square, where K is nothing but 1 by 4 pi epsilon naught, right? Now, if I take the small q on the left hand side, F by Q, this will give us a quantity, and that quantity is known as the electric field. And F by Q is nothing but the electric field at that point due to whom? Due to the source charge. So, you can see on the right hand side, capital Q is the only parameter on which and the position at which it is dependent. Both are inverse square laws, means R, it depends on R. If you increase, electric field will decrease gradually. Clear? So, this is our electric field. Any doubt? You can copy if you want to. Let's move to the properties of electric field. So, let me write some properties of electric field, then we will see how we can represent them geometrically. Okay. So, let's write here properties of electric field. Properties of electric field. Very important for problems. So, let's see the first property. If Q is unity, if the charge, small charge Q is unity, let's go back to our expression. Small q is unity, which means the electric field is equal to the force, right? Because if q becomes 1 over here in this expression, then this expression converts into electric field and F will be equal to E, right? So, if q is unity, the electric field due to charge q is numerically equal to force exerted by it. This is the first point.
Let's see the second point. The second point over here is the electric field E. The electric field E due to Q, due to capital Q, is independent of test charge. That we have seen in the expression as well. Independent of test charge small q. Sir, how? Simply we know the expression. Our expression of E is nothing but K capital Q by R square. It doesn't contain any small q. So let's see the next point. This is the second point. Let's see the third one, and very important here. Important point. For a positive charge, the electric field will be directed radially outward from the charge, away from the charge. We will see that in field lines. For the time being, we just take that it is radially outward for a positive charge. What about negative charge? For a negative charge, the electric field will be directed radially inward towards the charge. These are just conventions. These are called properties of electric field. Yeah. Let's see now, how do we represent an electric field? So, electric field is represented by, the geometrical representation of electric field is known as electric field lines. Sir, what are electric field lines? They are just a geometrical representation of electric field. So, these are geometrical representation of electric field. So, you represent it. Do electric field is a real thing? Yes, electric field is a real thing. Is electric field lines a real thing? No, they are just representation. So, how do we represent, sir? If you take a positive charge, you can represent it like field lines like this. They are radially away for a positive charge. We will see problems based on these field lines. They will be used in the applications in the upcoming part. For a negative charge, they are radially inward towards the negative charge. But if there is a positive and a negative charge, and we will see such a system, we call it as a dipole. We will talk about electric dipole after a few minutes. So, if there is a positive and there is a negative charge, the field lines will go from positive to negative. So, they are going like this, they are going like this away from this, and here it is coming inside towards the negative charge. So, this is the way we represent electric field lines for a electric dipole. Exactly, quite similar but not exact. That we will see in the magnetic field lines, because that is the differentiator. Okay, there will be a different thing which will be like quite different in case of a magnet. Done? Yeah. Now the most important part for CBSE, they often ask this question, that is properties of electric field lines. That's very important. Properties of electric field lines. Electric field lines. Let's see what are the different properties of electric field lines. So the first property that we know, that is field lines. Okay. Start from a positive charge. Start from a positive charge and ends at if there is a negative charge. If there is no negative charge, they will go to infinity. Okay. So let me just write this also. If there is a single charge, they may start, in case of a negative charge, they might come from the infinity. So they may start from infinity, and for a positive charge, they may go and end at infinity. So that is the situation for first property of field line. Let's see the second part. If let's say there is a no charge in between, there was some charge which is placed at my home right now, let's say. Outside my home, there is no other charge. In such a place where there is no charge, then these field lines which were coming out because of some particular charge, so in a region free from charge, electric field lines can be taken to be continuous curves. They are continuous without I'll explain, without any breaks. So what can't be possible? If this is a positive charge, the field line which is going from here can be like this, can be like this, but it can't be like this. You can't have breaks. It can't be like this. This is not possible. Your field line cannot be like this. Though they are going away from the charge, but still there are breaks in between. So breaks are not possible if there is no other charge. If there is another charge that we have seen in a dipole, that we will see later on again. So this is another property of electric field line. Let's see the next one. Next one says two field lines can never cross each other. Can never cross each other. Now this is crucial one. This is the mostly asked property of electric field lines. Two field lines can never cross each other. Now question is why? They ask this question in 1 mark also, separately, not asking in properties of field lines, but they can ask you in 1 mark question that why two field lines can never cross each other? Because, this is the reason, because if they did, the field at the point of intersection will not have a unique direction. Now, so what does it mean? It simply means, let's say there was a field line which was coming from any positive charge or a negative charge, or it is going outward, let's say, like this. Another field line, let's say this is the second field line which is going like this. Now, I am assuming that these two cross each other. Now, if they are crossing each other, they are crossing it at any point P. Now, if I release a charge, at this point. Now, according to Coulomb's law, it will experience a force. So, this electron will go along this direction. And if I release an electron over here, it will go along the field line like this direction. But if the same electron, if it reaches at point P, it gets confused. Like it should go along the pink one or the red one. So this confusion arises because of the intersection. Because point P doesn't have a unique direction. Every point has a unique direction. If a train is moving on the red path, it knows that it will go along this direction. If I release it at any point, I know that it will go along this direction. No other point. And if there is a train which is moving on the pink path, we know that it will move along this direction. But if the train reaches point P, you can't say that it will go along the pink or along the red until you know the past, right? So P is not having a unique direction. Hence, no two field lines can cross each other. So this is a very important and often asked property of field line. Finally, the last one, and the last one says field lines do not form any closed loop. Now, sir, what do you mean by closed loops? Simply, a field line can never look like this, that it went from here and it came back here. No loop like this. Or it is like one field line is going like this, another one is going like this, and one field line is going like this. No, this is not possible. First one is possible, second one is possible, third one is not possible. So, such fields we can't have. So, field lines can never have closed loops. These were our properties of electric field lines. I'll move to the next topic. Let's see our next topic. Our next topic is an electric dipole. So, let me just write here electric dipole. Sir, what is an electric dipole? An electric dipole, it's a pair. It's a pair of equal and opposite charges Q and minus Q separated by a distance 2a. Okay. So, before I explain, just focus on this part, that we are dealing with two charges which are equal and opposite. So, sir, can it be Q, 2Q and minus 2Q? Yes, of course, this is an electric dipole. Sir, can it be 5Q and minus 2Q? No, it can't be an electric dipole. Sir, equal and opposite. So, sir, can it be 5Q and 5Q? No, still it is not opposite. Be very careful. It should be equal and opposite. So, these are the conditions. Can it be minus 2Q and minus 2Q? No, it's still not equal and opposite. So, an electric dipole, the very basic definition of electric dipole is the charges should be equal and opposite. And they are separated by a certain distance. So, sir, if they are separated by a certain distance, why you are taking that distance as 2a? We are taking this distance as 2a because when we will derive some expressions, we will require the separation from the midpoint of this dipole. So, you can also call it as L, that's also fine, 2a or L, that's okay. But we usually take it as 2a because this 2a, when you take it from midpoint, this gap becomes a and this gap becomes a, instead of writing a by 2, a by 2. Exactly. So, instead of making L by 2 or A by 2, we just take the whole thing as 2A. So, that when you want to take the separation from midpoint, exactly, it will be that thing. But because this is done in class, okay, like 2A, most of the students, they make it wrong. Like if they are given the separation between the two charges as 10 centimeter and define the dipole moment, we will talk about dipole moment, there they will directly multiply 10 with 2. I don't know why. So, be very careful. 2a is the separation between the two charges. So, dipole moment, let's talk about dipole moment. So, dipole moment over here, we define a quantity. We will understand the core concept of that later on. Okay, so right now dipole moment we can define it as a vector quantity P, and that can be defined as, that is dependent on the configuration or geometrical configuration of this dipole, that is 2a, the separation, into Q. Now 2a is the total separation. Be very careful. If it is 10 centimeter, you have to take here 10 centimeter straight away. No need of multiplying it with 2 or no need of dividing it by 2. Straight away 2a, 10. Okay. Q is charge. Now we take the magnitude. We don't take the direction. Why? Because direction is always from negative to positive charge. That's a dipole. Okay. Now if you look at the unit of dipole moment, that will be nothing but unit of dipole, this charge, Coulomb, and unit of distance is meter. So be very careful. It looks like centimeter, but you have to keep the capital C. Okay. So this is our dipole and dipole moment. Unit of electric field is, so we know that electric field E, that is nothing but F by Q. F is the force and Q is the charge. So unit of F is newtons and Q is coulomb. So Newton per coulomb is the correct answer in this case. Let's see the next one. Yes. So electric field due to a positive charge is radially outward. Let's see the next one. Electric field is real. That's true. Electric field lines are imaginary. See, so the question says here, electric field due to a 10 coulomb charge. So let me just write what is given. Q here is 10 coulomb of charge at a distance. So R is given here as 3 meter. So straight away we have a formula, E is equals to K Q over R square. So K is nothing but 9 into 10 to the power 9. Q, the charge, is nothing but here 10 coulombs, and R here is 3. So 3 square is 9. So we will get 10 to the power 10 Newton per coulomb. That's our answer, option A. Electric field due to 100 microcoulomb charge at a distance of 3 centimeter. So let me write here Q is 100 microcoulomb. So micro is 10 to the power minus 6 coulomb, and distance, let's write it R as 3 centimeter, which is 3 into 10 to the power minus 2 meters. Now the electric field E will be nothing but K Q by R square. And that will be equal to, what is our K? 9 into 10 to the power 9. Q over here is 100 into 10 to the power minus 6 whole divided by R square. So let's make it as 9 into 10 to the power minus 4. So 9 and 9 gets cancelled, and what we left with here is 10 to the power 9 and 10 to the power minus 6. That's 10 to the power 3 into 100, and 10 to the power minus 4 goes up. It will be plus 4. So 4 and 3 is 7, 7 and 2 9, 10 to the power 9 Newton per coulomb. That's our correct answer, option B. Electric field due to 50 nanocoulomb. So let's write here Q, that is equals to 50 into 10 to the power minus 9 coulomb charge at a distance. So R will be equals to 5 centimeter. 5 into 10 to the power minus 2 meter is, so electric field E, that will be equals to K Q over R square. K is nothing but 9 into 10 to the power 9. Charge over here is nothing but 50 into 10 to the power minus 9 whole divided by R square, which is 25 into 10 to the power minus 4. Now we can cancel 25 and 50. That will give us 9 into 2, and 10 to the power plus 9 and minus 9 goes, and here you left with 10 to the power plus 4. So 18 into 10 to the power 4 Newton per coulomb. That will be the correct answer, which is option B. Let's see the next one. If the electric field due to 0.1 coulomb, so Q here is 0.1 coulomb, charge is 1 Newton per coulomb. That's our electric field. So E is equals to 1 Newton per coulomb at any point X. So we have to find the distance. R is nothing but X. So E will be equals to K Q over R square. E is nothing but 1. K is nothing but 9 into 10 to the power 9 into Q. Q is 0.1 whole divided by X square. So X square will be equals to 9 into 10 to the power 8, because 0.1 will be 10 to the power minus 1. So I just took it as that. So if you take the root, X will be equal to square root of 9, that's 3, square root of 10 to the power 8, 10 to the power 4 meter. That's the correct answer. So option C. If the electric field due to 10 to the power minus 5 Coulomb, so that's our charge Q, that is equals to 10 to the power minus 5 Coulomb, and electric field here is given as 9 Newton per Coulomb, then find the point X. So let's assume R as X. So electric field E is nothing but K Q over R square. So E is 9, K over here is 9 into 10 to the power 9, charge Q is 10 to the power minus 5, and R is nothing but X square. So X square will be equals to here 9 and 9 gets cancelled and 10 to the power 4 we left with. So X is equals to 10 to the power 2 meters, which is 100 meters, and that is option C. So here the question says if the electric field due to a charge Q, so let me write here the charge is Q at a distance R equal to 3 meters, and E value is given here as 9 Newton per Coulomb. The value of Q they are asking. So let me write the formula. It is KQ by R square. Now what is electric field here? 9. K is 9 into 10 to the power 9. Q we are looking for, and R is 3. So 3 square is 9. So that will become 9 into 10 to the power minus 9. That will be our Q, or you can say 9 nanocoulombs. So that's option B. So question over here says, if the electric field due to a charge Q, so capital Q is Q, at a distance 9 meters, so R is 9 meter, and the electric field E is nothing but 5 into 10 to the power 9 Newton per Coulomb. The value of Q they are asking. So electric field E is nothing but K Q over R square, and electric field is what? 5 into 10 to the power 9. K is 9 into 10 to the power 9. Q we are looking for, and R is 9. So 9 square is 81. So we can cancel 10 to the power 9 both the sides. So it will be 5 into 81 over 9. That will be our Q. So 9 9s are 9 5s are 45, and 45 Coulomb is the answer for this option C. So the question over here says a 2-point charge is plus 5 into 10 to the power minus 19 Coulomb. So let me write here, this is 5 into 10 to the power minus 19 Coulomb, and plus 20 into 10 to the power minus 19 Coulomb are separated by a distance of 2 meters. So let's say the gap between the two is 2 meter over here. The point on the line joining them at which the field is 0, electric field intensity is 0. So let's assume that this point over here is point P, where the field is 0. Now if the field due to the charge A at P is 0, let's assume that this distance is X. We don't know this distance. If this is X, then the other one will be 2 minus X. Simple, right? Now since they are vector quantity, first draw the direction. Now if it is a positive charge, the field due to the first charge will be outward, radially away from the charge. For charge B, again it is radially outward, so electric field due to B is this side. Now we can see the angle between them is 180 degree, hence the net electric field at point P will be EA minus EB you can do, or you can do EB minus EA, doesn't make any difference. But we know that electric field at point P is 0 as per the question. So it will be EA minus EB. So if we take EB on the other side, it will be EB equal to EA. Now let's substitute the value of EB and EA. EB, electric field due to B at point P, will be K. Let me put here K. The charge is Q, 20 into 10 to the power minus 19 upon the separation, that is 2 minus X whole square. That will be equals to K, the charge on A, that is 5 into 10 to the power minus 19 whole divided by the separation, which is X square. Let's cancel out K with K, and 10 to the power minus 19 with 10 to the power minus 19. What we left with here is 20, let's take 5 on the left hand side, and 2 minus X whole square divided by X square. So this will be 20 upon 5, that is 4, that will be equals to 2 minus X whole square over X square. Now taking the root on both the sides, it will give us 2, that will be equal to 2 minus X over X. So 2X will be equals to 2 minus X, or 3X will be equal to 2, so which implies X is 2 by 3. Now be very careful, you can also find one more value if you take here minus 2, because root of 4 is minus 2 also, but that will give you a negative value. So here it is x equal to 2 by 3, which is option B. So question over here says 2-point charges. Let's call this as 0.2 Coulomb and another one is 0.4 Coulomb. They are placed over here at a distance of 0.1 meter apart. The field at the midpoint between the two charges. So if this is a charge A, this is charge B, and let's say this is our midpoint over here. So let's call this midpoint as point P. Okay. Now this positive charge, the field will be radially outward. So this will be electric field due to A, and due to this 0.4, it will be radially outward. That will be electric field due to B. So net electric field at point P will be equals to EA minus EB, we can think of, or you can say EB minus EA. That is just a matter of direction resultant depending on which one is greater, right? So EA is K QA upon R square. R will be AP, okay? Let me just make it AP only for the beginning, AP square minus K charge on B upon BP square. Now we know that it's a midpoint. So for midpoint, it's the same thing, right? AP and BP is same. So we can take it as K upon AP square. I am taking common. We left with QA minus QB. So now K is nothing but I am just solving it here. So which equals to 9 into 10 to the power 9 over AP. That is midpoint of 0.1. So 0.1 divided by 2 whole square. Okay, we will convert it now within a minute. QA is what? 0.2 minus 0.4. Okay, now we can see that it's a negative, so better we would have done QB minus QA. Okay, that's fine. Okay, so this will be 9 into 10 to the, yeah, anyways we take magnitude, so we will just remove the negative sign. So here it will be 0.01 whole divided by 4. So that, let's take that 4 straight away on the top, into 4 multiplied with 0.2. I am taking the magnitude here. So removing this point, you will get here 100. So let's see what we left with. We left with 9 4s are 36, and 36 into 0.2, that's 7.2 into 10 to the power, how much? 11 Newton per Coulomb. And that's, is there any option? Yeah, option A is the correct one. Understood? 2-point charges, 10 microcoulomb. So let's say this is our 10 microcoulomb over here, and another one is 40 microcoulomb over here. They are placed at a distance of 20 meter apart, right? So there's the point on the line joining at which the electric field intensity is 0. So let's say that this point P is the point where the electric field is 0. And let me call this as charge A and let me call it as charge B. Now electric field due to A will be radially outward. Electric field due to B will be radially outward. So electric field at point P will be equals to electric field due to A minus electric field due to B. Now it's already given that EP is 0. So let's straight away put here 0 will be equals to EA minus EB. And take EB on the left hand side, it will be EB equals to EA. Now EB will be equals to K QB upon BP square, and that is equals to K QA upon AP square. Let's take that AP is X, so this will be 20 minus X, right? So K and K will get cancelled both the sides, so K gets cancelled here and here. QB, the charge on B, is nothing but 40 microcoulomb, so 40 into 10 to the power minus 6 whole divided by 20 minus X whole square. That will be equals to 10 microcoulomb, 10 into 10 to the power minus 6 whole divided by X square. Let's remove this 10 to the power minus 6 with 10 to the power minus 6 and cross multiply. So 40 over 10 will be equals to 20 minus X whole square divided by X square. Cancels, and now take root both the sides. So root of 4 is 2. That will be equals to 20 minus X over X. That will be 2X. That will be equals to 20 minus X. And 3X will be equals to 20, which implies X is equals to 20 by 3 meters. That's the correct answer. Okay, so question over here says 2 point charges minus 10 nanocoulomb and minus 90 nanocoulomb are placed 80 meter apart. So let me just write here minus 10 nanocoulomb and over here it's minus 90 nanocoulomb, and both are placed over here at 80 meter apart. Okay, fine. The point on the line joining the two charges where the field intensity is 0. So let's assume that the field is 0 at point P. Okay, now and that's at a distance of x. So here it will be how much? 80 minus x from charge B. So from charge B it is 80 minus x, from charge A it is x. So let's draw the directions. Both are negative charges. So electric field at point P due to charge at A will be radially inward towards the charge. So this is EA. And electric field due to the charge B, that is again negative. So it will be EB in this direction. And since the angle is 180 degrees, so we can say that EA minus EB at point P will be 0. That will be resultant. So EA here will be equals to EB. And that implies EA is nothing but K charge on A upon separation AP square. That must be equals to K charge on B over BP square. K and K gets cancelled over here. QA charge on A, that's 10 nanocoulomb, 10 into 10 to the power minus 9 upon AP is x square. That must be equals to 90 into 10 to the power minus 9 whole divided by 80 minus x whole square. Let's cancel out this with this, and cross multiplying we will get here 80 minus x whole square whole divided by x square will be equal to 90 over 10. Let's cancel out 0 with 0, and taking the root it will be 80 minus x whole divided by x must be equal to 3. So 80 minus x must be equal to 3x, and that will give us 80 equal to 4x. Hence x is 20 meter. That's our correct answer. Option B. Let's move to the next one. Okay, let's see here. The question says 2 point charges are placed as shown in the figure. The net electric field due to both the charges at point P. Now first of all 20 nanocoulomb, as we can see the 20 nanocoulomb is positive charge, so it will be radially outward, so it will be like this. This will be, let's call it as A, let's call it as charge B. So electric field due to A will be EA, and the electric field due to B, that also will be radially outward, so that will also point in this direction. Let's call it as EB. Now since they both are pointing in the same direction, net electric field E must be equals to EA plus EB. And EA is nothing but K charge on A upon separation AP square plus K charge on B whole divided by BP square, because the separation is BP. Now K is common in both of them, so let's write here 9 into 10 to the power 9, that's K value, and QA is 20 nanocoulomb, so 20 into 10 to the power minus 9 whole divided by AP, that's 2 square, plus the second charge is 32 into 10 to the power minus 9 whole divided by BP, that's 4 square. Any doubt? Now here we can take 10 to the power minus 9 out, and that will cancel out. So this E total will be equals to, we can write here 9, and 10 to the power 9 and 10 to the power minus 9 will go, and we left with here 20 over 4 plus 32 over 16. 20 over 4 is nothing but 5, and 16 twos are. So 5 to 7, 7 nines are 63. So E total will be equals to 63 Newton per Coulomb. That's our correct answer. Option C. Any doubt? So question over here says 2 point charges plus Q and 4Q are separated by a distance of 6A. So let me just draw this. Let's say this is our Q and let's say this is our 4Q, and both are separated by a distance of 6A. So let me just draw here as 6A. The point on the line joining the two charges where the field is 0. So let me just take it as A and let's take it as B, and the point at which the field is 0, let's call it as point P, and let's assume that this is at a distance x, so this will be 6A minus x. So point P, the electric field is 0, electric field due to the first charge, both are positive, so it will be radially outward EA, and due to B, it will be radially outward in this direction EB. So net field at point P will be equals to EA minus EB because they are both in opposite direction. 0, that will give you EA minus EB, or we can write it as EB equals to EA. Now what's our EB? Electric field at due to B, that will be K. The charge is 4Q upon separation is 6A minus X whole square. That must be equal to K, the charge on A, which is Q, upon how much? X square. So K cancels with K, Q cancels with Q, and let's cross multiply. So 4 will be equals to 6A minus X whole square whole divided by X square. That will be 2, that will be equal to 6A minus X whole divided by X, and that would give us 2X is equals to 6A minus X. 3X will be equal to 6A, and X will be equal to 2A. That's our answer. So correct answer is option B. So question over here says 2 point charges are placed as shown in the figure. The net electric field due to both the charges at point P. So first of all, due to minus 36 nanocoulomb, it will be radially inward towards the charge. So let's call it as A, let's call it as B. So it will be electric field EA. That will be towards the charge because it's negative. For the second charge as well, it will be towards the charge, and this will be EB. Correct? So the net field at point P, that will be the sum of EA plus EB. Right? And EA is nothing but KQA whole divided by AP square plus KQB whole divided by BP square. Let's take common out here. K is 9 into 10 to the power 9. QA is nothing but 36. Do we have to take negative sign? No, because we have already assumed it in the directions, right? So AP is nothing but 6. So 6 square plus QB, that's 12 into 10 to the power minus 9 whole divided by the separation between B and P, 2. So that's square will be 4. Let's take now, let me solve it here. So net electric field at point P will be equals to, let's take 10 to the power minus 9 common out and cancel with 10 to the power plus 9. So it will be 9 into 36 over 36 plus 12 over 4. So that will give us 9 into 36 over 36, 1 plus 3. So that will be 36 Newton per Coulomb. That's option A. Understood? Okay, so the question says 2 point charges are placed as shown in the figure. The net electric field due to both the charges at the midpoint. So midpoint, let's assume that this is our midpoint over here. And at this midpoint, let's call it as P, let's call it as A, let's call it as B. And the field due to the negative charge, minus 36 nanocoulomb, will be radially inward. And let's call it as EA. Electric field due to B will be towards the charge B, that will be EB. And since the angle between them is 180 degree, the net field at P will be equals to EA minus EB. And EA is nothing but K charge on A whole divided by separation, which is AP square, minus K charge on B whole divided by BP square. Now what's common in both? Common in both is K, and AP and BP are equal because it's a midpoint. So let's call it as K upon AP square is common out. We left with charge on A minus charge on B. So let's substitute the values. K is 9 into 10 to the power 9. AP square is nothing but 2 square, which is 4, into charge on A, 36 nanocoulomb. So let's call it as 10 to the power minus 9 minus 12 nanocoulomb, which is 10 to the power minus 9. Let's take 10 to the power minus 9 common out, and that will cancel out, and we left with 9 by 4 into 36 minus 12. 36 minus 12 is 24. So that will be 6 9s are 54 Newton per Coulomb. That's option B. So let's see the question. Question over here says 2 point charges of 6 microcoulomb. So let me just draw here. This is 6 microcoulomb and 24 microcoulomb. So let's say this is 24 microcoulomb are separated by a distance of 6 meters. So let's say this is our 6 meters. The point on the line joining them where the field is 0. Let's take this as P. Let's say this is A. Let's say this is B. And let's say P is where the field is 0. So this is X. This will be 6 minus X. So the net field at P is 0, which means EP. Now electric field due to the first positive charge radially outward, so this will be EA, and electric field due to B, that will be radially outward, EB. So net field at P will be EA minus EB. Now EA is nothing but K charge of A upon the separation AP square minus K QB upon BP square. Now since it is 0, let's put it 0 and take it on the other side. So K will get cancelled and we left with QB upon BP square will be equals to QA upon AP square. Now QB is nothing but, let me solve it here, QB is nothing but 24 microcoulomb, so 24 into 10 to the power minus 6 whole divided by BP. BP is nothing but 6 minus x whole square, which is equals to charge 6 into 10 to the power minus 6 whole divided by x square. Let's cancel out this with this and cross multiply. So 24 by 6, that will be 6 minus x whole square upon x square. 24 upon 6 is 4, and taking the root, it will be root of 4, which will be equal to 6 minus x upon x, and root of 4 is 2. So 2x equals to 6 minus x. 3x is equals to 6, which implies x is equals to 2 meter. That's option C. The question says over here, 2 point charges 2 microcoulomb, so 2 into 10 to the power minus 6 and 50 microcoulomb, 50 into 10 to the power minus 6 are separated by a distance of 24 meters. So this separation is 24 meter. The point on the line joining them at which the field is 0. So let's assume this is point P, this is our A, this is our B, and electric field at point P is 0, which means EA must be equals to EB. And since they are positive both, so the field direction will be radially outward. So it is EA, this is EB, and let's put here values. K cancels with K both the sides, so charge Q upon R square, which is x square. Let's assume this is x, and that will be 24 minus x of 50 into 10 to the power minus 6 whole divided by 24 minus x whole square. Let's cross multiply. So 24 minus x whole square upon x square will be equals to 25. So taking the root both the sides, it will be 24 minus x over x will be equal to 5, and that will give us 24 minus x will be equal to 5x, and 24 equal to 6x, which means x is 4 meters. That's our correct answer. Option B. Okay. So in the last lecture we did electric dipole. Now today we will find electric field due to an electric dipole at different points. Okay. Dipole, we have already discussed in the previous lecture. I am just repeating again. It is a pair of equal and opposite charge Q and minus Q separated by a distance 2a, right? And here what is important parameter for this is electric dipole moment, and electric dipole moment is given by P, which is equal to 2aq, and the direction is always from negative to positive. Be very careful with this particular thing, right? So let's find now our first derivation in this chapter. Okay, very important derivation, that is our electric field due to an electric dipole on the axial plane, So let's see what is electric field due to an electric dipole on its axial plane. Very important, but very important derivation. Okay. So let's see. This is our minus Q charge and this is our plus Q charge, and they both are separated by a distance 2a, because this is our electric dipole, right? Now we are finding the field at axial plane. What is axial plane or what is axial point? Axial plane or axial point is a point along the axis of the dipole. And what is the axis of the dipole? This direction. So we will draw a point over here, and let's say this is our point P at which we are finding the electric field due to this dipole. What is important here is this point P, the distance we will take will be from the center of the dipole. So this gap is our R. So this is our center. So from here, if this is R, this gap is let's call it as A, let's call it as B, let's call it as O. OB is nothing but A, and AO is nothing but A, right? So as we have done in the previous problems, numericals also, let's first find the direction. So electric field at point P due to charge placed at A will be towards the charge, so it will be EA. Electric field at point P due to the charge at B, which is radially outward, so it will be EB. The angle between EA and EB is 180 degree, and if two vectors are aligned at 180 degree, the resultant electric field at P will be EA minus EB. EP is the axial point, right? And that will be EA minus EB. Now you can also do EB minus EA, okay? So better is to choose EB minus EA instead of EA minus EB. Sir, why? Because you can see that the charge B is closer to point P, so the intensity of electric field will be more compared to the charge at A. So EB minus EA will be a better choice. Otherwise you will get a negative sign, so it doesn't make any difference. That magnitude we can remove that. So EB, let's find EB. So EB will be charge K, the formula for electric field is K, charge on B, that's Q, whole divided by the separation, that is BP square, minus K Q, again I am repeating, we will not take the negative sign, okay, whole divided by AP square. Any doubt? So let's take KQ common. So KQ taking common, here we left with 1 by BP square minus 1 by AP square. Now, what is, sir, BP? So this K, I am just writing it as 1 by 4 pi epsilon naught. Charge is Q. BP. Now, if you be very careful, BP is nothing but 1 upon R minus A whole square. That's our BP square. And what is our AP? AP is 1 over R plus A whole square. This is our electric field. Let's simplify it further. So here on simplification, this will give us Q over 4 pi epsilon naught, multiplying, cross multiplying, it will be R plus A whole square minus R minus A whole square, whole divided by, cross multiply them, it will be R minus A whole square into R plus A whole square. I hope this is clear. Now, let's simplify it further. It will be Q over 4 pi epsilon naught. Let's expand the numerator, A square plus B square plus 2AB minus A square minus B square plus 2AB. Be very careful. I have directly opened it because the signs will flip. Now, in the denominator, if you be very careful, we can rewrite this expression as R minus A, R plus A whole square. Sir, how can you write that? X square into Y square will be written as X into Y whole square. Yes, so that's the same thing. So here, let's simplify it further. So it will be Q over 4 pi epsilon naught, and let's cancel out R square with R square, A square with A square. We left with 4AR upon R square minus A square whole square. And 4AR, that can be splitted as Q upon 4 pi epsilon naught. We can split 4AR as 2 into 2AR upon R square minus A square. Any doubt? 4A is nothing but, why we are splitting it? That's a good question. So it will be 2AQ into R whole divided by 4 pi epsilon naught into R square minus A square whole square. And what's our 2AQ? That's our dipole moment. So net electric field at any point on the axial point at a distance of R will be 2P, be very careful, R upon 4 pi epsilon naught R square minus A square. That's our outcome of electric field on the axial plane. Now, if there is a condition, if R is very, very far away, R is much, much greater than A, then R square will be much, much greater than A square. then r square minus a square will be approximately r square only, right? And in that case, our net electric field will be rewritten as 2pr upon 4 pi epsilon naught r square whole power 4. We can cancel the numerator 1 of the r, and we got, for an assumption that if r is much greater than a, then it will be the, this r will be removed and this will be r cube. So electric field is inversely proportional to r cube for a dipole. And from where we got? Yeah. Exactly. R square whole raised to 2. Okay. So that will be our So what we conclude up till here is electric field due to, I'll go to other side. So electric field, what we conclude that electric field E due to a single charge is 1 by 4 pi epsilon naught q by r square. But what we got for an electric field due to a dipole on a axial plane. So let me just write here dipole, and along with this dipole on the axial, because one more point we will find in the next lecture. So that we found as 1 by 4 pi epsilon naught, and how much we got? 2p by r cube. So for a single charge, it is inversely proportional to r square. But moment the charge increased, it became a dipole, it became inversely proportional to r cube. Understood? Yes. Our next topic is electric field. Let me just make it a little more zoomed. Okay. So next is electric field due to an electric dipole. Electric dipole on its equatorial plane. Okay, so let's start with this new topic. So in electric field due to electric dipole on its equatorial plane, first let's understand what is an electric dipole. We have already discussed it before, but let me just remind you that if we have a pair of a positive and a negative charge, so let's say this is plus q and this is minus q over here, and both of them are separated by a distance 2a. Because we take the separation from midpoint, that's why we are assuming the separation to be 2a, right? And equatorial plane, that's a new term here. Equatorial plane, how do you define? Any point on the perpendicular bisector of this dipole. Perpendicular bisector means a line which is perpendicular to this dipole and perfectly 90 degree, and it is splitting this dipole into two equal halves. So that is A over here and that is A over this side also. Let me make it as A. Now, sir, this equatorial plane will be infinite. You can choose any point. So let's take a particular distance as r. This r is the distance separation from the midpoint of the dipole, right? Now let's figure out our directions. So we know that positive charge. Now positive charge, the electric field is radially outward in all the possible directions, right? But what we will do here is we will just draw a line joining the point at which we are finding the field like this, and along this particular direction we will find it outward. So this is our electric field due to the positive charge q. Now electric field due to the negative charge, how will you draw? So simply draw a straight line and towards the charge, exactly. So electric field will be in this direction, E minus q. That will be our electric field. Now if you have two vectors like this, one vector A and another vector B over here, then we know that the resultant of A and B will be along the line passing through the diagonal using parallelogram law of vector addition from 11. If you know that, that's fine. If you don't know, just remember that two vectors are aligned like this, then this will be the resultant R, right? So we will make use of the same concept over here. If EQ is in that direction, E minus Q is in this direction, then our resultant of both of them, that will be pointing in this direction. That will be our electric field E net, or the total electric field. Okay. Now, if such a scenario is there, then how do you find the total net electric field? So, for that we should know the angle between E minus Q and E plus Q. That is this complete angle. But that would be tricky if you try to figure out the angle like that. Better way will be like they have done. You can solve it using that theta also, but that will require a little bit of maths. So we will not do it because that's not in our NCERT. But we know that this is our angle theta over here, right? So if we assume that this is our angle theta, let's use Pythagoras theorem. So let me call this as A, let me call it as B. We know that, and let me call it as O. Let's see that AO is nothing but A. OB is nothing but A. And OP we can see it is R. So if you use Pythagoras theorem, this is nothing but root under R square plus A square. That will be our hypotenuse, right? And similarly, PB will be root under R square plus A square again, right? Yeah, using Pythagoras theorem. So if PAB is a triangle with two sides equal, then the angle opposite to equal sides will be equal. So this will be angle theta, right? So both angles are theta. If this is theta, then we know that this will be theta because this will be corresponding angle. To whom? E net is parallel to AB, right? So if E net is parallel to AB, then that will be corresponding angle. And if this is theta, then this will be also theta, that is alternate angle to same thing. Yeah, E net is parallel to AB, so alternate angle. So that will be theta. Okay, great. So we have already found our angles. Let's now see how to simplify. We will make use of our simple concept of 11th standard, that is resolution of vectors. Sir, what is resolution of vector? Let's simply draw an axis over here. Let's say this is our axis. Okay. So, and wait, let me just make it better. Let me just make it here. This is our straight line over here. And this is our y-axis and this is our x-axis. So, let me just make it like this. Okay, great. Now, we know that EQ is pointing in this direction. This is our EQ. And our E minus Q, that is pointing in this direction. So, this is our E minus Q, right? And this is our angle theta over here. And this is our angle theta over here, as per the diagram as we can see. And E net is pointing along x-axis, okay? So, we can split these EQ as in this side, the component of EQ will be EQ sin theta. And in this side, it will be EQ cos theta. And E minus Q, we can point it here in this direction, E minus Q sin theta. And the component of that will be this side as E minus Q cos theta. So, this will be the way we will make use of, though you don't have to draw the second diagram in board exams, right? You have to only draw the first diagram, okay? And let's see how to proceed. Let's find the magnitude of EQ. Now, if you remember that electric field of any charge is given by K, Q by R square. That's the electric field. So, let's use the simple concept for our first charge, that is positive charge E plus Q. Now, E plus Q will be equals to K, which is 1 by 4 pi epsilon naught. We have discussed in the previous lectures. The charge is plus Q and the separation here is AP square. And that we can write it as Q upon 4 pi epsilon naught. And AP is nothing but root under, so squaring the root will go and it will be R square plus A square. I hope this is clear, EQ, okay? Similarly, let's figure out E minus Q. So, E minus Q over here, that will be equals to same. We will make use of same above formula, 1 by 4 pi epsilon naught. Again, reminding you, the negative sign is not considered. So, it will be Q by BP square. Exactly. So, BP square. So, BP, which is again the same value, it will be Q by 4 pi epsilon naught, R square plus A square. I hope this is clear. Okay. EQ is clear and E minus Q is clear. Now, looking at EQ and E minus Q, we can see that both of them have the same magnitude. Yeah. Both of them have the same value, Q by 4 pi epsilon naught, R square plus A square. Now, looking at the second diagram, which is this diagram, what we can say here is EQ sin theta, which is pointing in the upward direction over here, and E minus Q sin theta pointing in the downward direction. Two equal and opposite directions and magnitudes are equal, right? So, these components will cancel out. So, no role of sin theta, both cancels out, right? So, net electric field will be here, will be E net. Let's write it as E net, and that will be our EQ cos theta. plus E minus Q cos theta. Only the cos components will survive because sin theta are cancelled out. Why? Magnitudes are same and directions are opposite. It's like at two forces, if somebody is pulling a table from one side with 10 Newton and another side also 10 Newton, the table will go nowhere, right? Because equal and opposite forces will cancel out. Now, EQ, we know that it's 1 by 4 pi epsilon naught and Q over R square by R square plus A square cos theta. And E minus Q is Q by 4 pi epsilon naught R square plus A square cos theta. Now 1 apple plus 1 apple, so 2 apples. So this whole thing is same, repeating itself. So 1 apple and 1 apple will add and that will give us 2q cos theta whole divided by 4 pi epsilon naught R square plus A square. I hope this is clear. Now if you look at our diagram, the first diagram, which is the most important part. For this diagram, our cos theta is nothing but base upon hypotenuse that we have learnt in class 10th. So which triangle to choose? Any triangle. AOP you can choose or BOP you can choose, doesn't make any difference. I am choosing the first one. You can choose the second one, you will get the same result. So base is AO and hypotenuse is AP. If you are choosing the second triangle, it will be BO upon BP. That will be similar. So AO is nothing but A and AP is root under R square plus A square. I hope this is fine. This is our cos theta. Now this cos theta we can substitute over here and we will get our expression for total electric field. That will be 2q upon 4 pi epsilon naught R square plus A square, and let me just separately write the cos theta value as A upon root under R square plus A square. Now this root under R square plus A square, we can rewrite it as R square plus A square power half because root is half. Here the power is half and here the power is 1. When you multiply both, the powers will add up. And that will be 4 pi epsilon naught R square plus A square whole power 3 by 2. Now that will not be our final expression. We'll just make a slight change over here. 2AQ. What is 2AQ? So 2AQ is a dipole moment. We have learnt in the previous lectures. 2AQ is dipole moment. So dipole moment, when I explained, I gave you the direction. Dipole moment always points from negative to positive. Always. Now look at the direction of dipole moment. Dipole moment is pointing from negative to positive. Electric field is pointing from positive to negative. So we will put, when you express it in terms of dipole moment, we will put a negative sign here because it is pointing in the opposite direction to the direction of net field. So from there this negative sign arrives and this will be R square plus A square whole power 3 by 2. Any doubt up till here? Now this is our actual electric field, but we will use a assumption that if we are finding very far away from the dipole, the electric field on the equatorial plane, then R will be much greater than A. And in that case, if R is much greater than A, then R square plus A square, that will be approximately R square. Let's substitute this value in this electric field. So E net will be equals to minus P whole divided by 4 pi epsilon naught R square plus A square, that will be R square whole divided by 3 by 2. Power 3 by 2, and that will be minus P whole divided by 4 pi epsilon naught square and 2 cancels R cube. So that's our E net for a equatorial plane. So two most important things you have to understand here, that for a dipole on the equatorial plane, it's minus P by 4 pi epsilon naught R cube, and electric field due to the same dipole on the axial plane, that will be 2P that we have discussed in the previous lecture, that is 4 pi epsilon naught R cube. So negative sign, and secondly here it is twice. So we can say that E axial, ignoring the negative sign, that's just a direction. So I am just taking the magnitude E axial upon E equatorial. That will be equals to 2. So axial, if they have given you equatorial value, you can simply multiply it with 2, you will get the equatorial plane. The red part which I have written, that you don't have to include it in the derivation. That is just an extra thing you have to remember for problems. But for derivation, you have to do in board exam up till here. Any doubt? You want to copy this? Okay, I'll move to the next topic. Let's see the next part. Okay. Let's see the next part. The next part is, okay, what we have discussed. Let's see a recap of what we have discussed in the previous lectures. Starting from the first lecture, I discussed that there are two types of charges, positive and negative. Let me remind you that positive charge is lack of electrons, negative charge is excess of electrons. Now, every charge has a field around it, and this field is responsible for an important part, which is force. And this force we have discussed as Coulomb's force. And this Coulomb's force gives you force between two charges at a time. That's very important, two charges, because students, they get confused that why we are making it more and more complicated. Because at the end of the remaining topics, they will focus on something different. And when we reach to that topic, many students have this doubt that why we are dealing such situations. We already have Coulomb's force, we can simply apply the formula and we can get the solution. But the problem is, Coulomb's force works for two charges at a time, and when you increase the charges, it becomes more complicated. We have done such problems like for a triangle, for a square. So, 4 maximum in board, they keep 4, but even if it becomes 5 and 6, it takes more and more time, okay, to solve using Coulomb's law. Now then, after that, we discussed a special type of configuration, that is dipole. Now, what's a dipole? A pair of charges, equal and opposite, okay, equal in magnitude, opposite in direction. Then we found the field due to dipole. Now, why we found the field due to dipole on the axial plane and on equatorial plane? Sir, what if there is neither axial nor equatorial or any random point here? That is discussed in NEET and JEE, okay, that we will not discuss for the boards. So, for equatorial and axial, they are unique positions corresponding to a dipole. Sir, what is a dipole in real life? A simple case of dipole is the salt, common salt, what we eat. So, if you take NaCl, yeah, common salt, if you put it in water, Na plus and Cl minus, that's an electric dipole. You will get a positive charged sodium and negatively charged chlorine. Now, that acts as a dipole. Now, if there is a dipole, then there is a field around it that just now we have discussed, we have figured it out, right? So, if there is a field around this, if you place a charge around this dipole, how that charge will behave? That's important. So, if you know the field, you can figure out the force, right? So, that was the concept of field. Now, next topic is, third important topic related to dipole is dipole in an external electric field. Now, if somebody is giving an electric field and if you place a dipole, what happens in that case? So, dipole in an external, and what's important about this topic is, it's a uniform field, external uniform electric field. That's a very crucial thing, uniform electric field, because if it is non-uniform, things will be little different, and that is not there in our NCERT, right? So, we will focus ourselves on uniform electric field. So, what's a uniform electric field? A uniform field will look like this. You have a constant value of field which remains constant and it doesn't change. If I completely fill this whole space with such a field, now you can't say that, though it looks like there are gaps, I am not putting these gaps, okay. So, this is like a uniform electric field. All over the space, you can't say where is the value, okay, now since I have colored it on, so it became little dark, but it is uniform, so the value will be same, okay. Okay, and if there is a field, now sir, who is applying this field? Maybe some charge, we don't care about that charge, but what we care about is, we know the value of this electric field and that is fixed. That's why it is called uniform. So, at each and every point, if I place it here, if I place it here, every place the field is constant, it is not changing. Can you give a particular example like 2 Coulomb, Newton per Coulomb or 10 Newton per Coulomb, any charge? Who is applying that? We don't care. We just care about that what is the value of electric field in this region, right? In such a region, if I place an electric dipole, let's say this is a charge plus Q and let's say this is a charge minus Q. And this charge is oriented at any angle. So, let me just make it 1 second, little specific. Okay. So, this is our dipole and the separation for this dipole is 2A. And let's suppose the direction of electric field is pointing in this direction. It's constant, all over constant, right? If I draw an electric field line over here, we can see that the dipole is making an angle theta with the electric field. And because of this theta, there will be something important which we will see. So just imagine that this is a magnetic field. Just imagine, because we have done that in 10th standard, this is a magnetic field due to a strong magnet. And we are putting another magnet which looks like this inside this field. What will happen? Sir, this will rotate. Sir, why it will rotate? Let's see. Let's see the core concept. So if electric field E is positive, this plus Q will repel it. So it will repel, let's say, in this direction. Right? And with what force? F equals to QE. That will be the force of this positive charge. If positive charge is repelled by the electric field, the negative charge will automatically attract, because that's in opposite direction. So that will be F equals to QE. Sir, why not negative? We are taking magnitudes. Direction is already given, right? Now, if I'm just reminding you the concept of 11th standard so that you can understand it better. If this is a table, I am applying a force of 10 Newton in this direction. Another person is applying a force of 10 Newton in this direction. Where will the table go? So it will go nowhere. It will remain there. Great. If this is the same table and instead of 10 Newton, I am just putting here 5 Newton. Where the table will go? So it will move in the upward direction. Yeah. And if I make this as 25 Newton, then it will go in the downward direction. Great. Now what is important here is this 25 Newton and 10 Newton are pointing in the same direction. What if the same table is here? Be very careful. I am applying a 10 Newton force in this direction and somebody else is applying a 10 Newton force in this direction, but provided it's not in the same point, the point of action is not same on the table. One is on this extreme end and another is on the other end. If some force acts like this, when it is not acting in the same point, though it is in the opposite direction, but it is not acting at the same point, what the table will do? What's the natural tendency? Sir, it will try to rotate. And this rotation is because of a new concept which we discussed in 11th standard, that is torque. So the same situation happens for this dipole. When a dipole is placed in an external uniform electric field, it experiences torque. It experiences torque. And torque from 11th standard is nothing but torque tau, that will be equals to force into perpendicular distance, or more being specific, R cross F, where R is the perpendicular distance along which, like if this is the length of the table, that will be R, being more specific, and force is the value, magnitude which you are applying here. So in this case of dipole, R is nothing but 2A and F is nothing but QE. Any doubt in this part? Now 2A into Q, 2A can be directly multiplied with Q. We can pair it up with Q. Why? Because Q is a scalar quantity. You can take it. So we can't directly make it as 2AE, but we can make it as 2AQ cross product with E. Be very careful. This is not multiplication. This is cross product. So 2AQ is nothing but P cross E. And P cross E is nothing but PE. Magnitude. I can put here two magnitude signs. And here it is sine of angle theta, where theta is what? So theta is the angle between the electric field and the perpendicular direction, or the direction of the length of the dipole. Great. So sir, what happens if theta becomes 0 degree? If the dipole is aligned along the field, then theta will be 0. So let me just write here, if theta becomes 0 degree, sine theta will become 0. And in that case, the torque will be 0 experienced by the dipole. If the theta becomes 180 degree, just opposite, then sine 180 is again 0. So torque again will be 0. What about theta is 90 degree? If theta is 90 degree, then sine theta will be 1. That's the maximum value of sine. And torque will be maximum, in this case PE. That will be maximum, I am writing here. So they can ask you, when will a dipole will experience a maximum torque? theta is 90 degree. Now that's, I think, enough for boards, but now looking at the papers this year and all, we can say that we can understand one more very small concept, that what happens if instead of uniform, it's a non-uniform field. So which means the electric field at each and every point is different, right? So let me write here only one statement. I'm just putting it extra in by any chance if they ask for a non-uniform electric field. For a non-uniform electric field, electric field value at each and every point will be different. So if electric field value is each and every point is different, then the force experienced by this minus q charge, that will be different from the force experienced by the plus q charge, because the electric field values are different, right? And in this situation, there will be two things happening along with the torque. Force will be experienced. Along with the torque, a force will be experienced. That will be the case in case the field is non-uniform. That will be very important case for NEET and JEE. Any doubt in this part? I'll remove this. I'll move to the next part. Let's understand the next concept, and our next concept is of, okay, so up till here we discussed about charges like 1, 2 or dipole or 3, 4 maximum charges. Now we will not count it like that. Now we will have continuous charge distributions. We will call it as continuous charge distributions. Let's understand what is continuous charge distributions. Okay. Because in real life, we mostly find continuous charge distribution. We don't find single charges. Okay, because there are millions and millions of charges which are moving. Okay, we have discussed this in the first lecture, that one ampere or 1 coulomb of charge is transferred. We say that 6 into 10 raised to 18 electrons are transferred, right? And 6 into 10 raised to 18 is enormous, right? So continuous charge distributions are the scale at which we are dealing in the real life. So give an example. For example, number of hairs on your head, that is continuous. You can't count. Now that doesn't mean they are infinite, right? They are finitely infinite. So finitely infinite means something which is uncountable, but still we can count if we have that much of time, right? Yeah. So continuous charge distribution is somewhat like this. Like if I take a metal sheet and I completely charge it. Now I don't know how many charges are there, but we can draw it like this. There are a lot of charges are there. Lot of means a lot of. Like the number of stars in this space. So can we count stars? Of course you can count stars. For that you need to do graduation in physics so that you can understand what are the statistical methods in which we can count stars. Right? So if you take instead of sheet, if I take a rod, this rod is completely charged. If I take a spherical ball, this is completely charged. So such distributions are known as continuous charge distribution. And in continuous charge distributions, there will be mostly 3 cases. The first case is, we call it as linear charge distribution. Linear charge distribution. If the charges are along the length, let me write the definition also. If the charges are present along the length of an object, such distributions we call it as linear charge distribution. Any doubt? Next is surface charge distribution. Surface charge distributions. If the charges are present along the area, if the charges are present along the area. Like a sheet. Okay, I'll refocus on these things. Let me just write the definitions. Volume charge distribution. If the charge are present along the volume. Now, be very careful when you are dealing with these three. You can simply see that this is one dimensional, this is two dimensional, and this is three dimensional. Though our course focuses mostly on 1D and 2D, though we will discuss 3D also a little bit 3D, but numericals mostly bases on 2D, right? So we will focus on these things 1D, 2D, 3D, one dimensional, two dimensional, three dimensional. But in real life, if we focus, there is nothing known as 1D and 2D. Because if you look at a simple wire, this wire itself has an area of cross section. So that's a 3D, right? Because that's why we can simply hold it, okay, we can cut it, we can do anything because that's a 3D, it's not a 1D. But what happens that if wire we are taking, considering like in the line which I have drawn here, it looks perfectly 1D because the length is more prominent factor other than area and any other parameter, right? So charges are mostly distributed along length. Now similarly, if I take a paper sheet, the thickness, if you ignore the thickness, because though thickness is negligible compared to the area, so the length and breadth becomes prominent but height becomes negligible. So that's a 2D. When similarly, if you take a 3D, it will be a cube or cuboid. Length becomes prominent, breadth becomes prominent, height becomes prominent. But be very careful, students have this such kind of questions that, sir, why 1D? We don't have 1D in real life. Though you don't have, but the charges are mostly distributed along the length. The area of cross section is negligible, so we don't care about that when we are taking it as macroscopic variable, right? So be very careful with this. So if the charges are present along the length, we call it as linear charge distribution. If the charges are present along the area, we call it as surface charge distributions. And if it is present along the volume, we call it as volume charge distributions, right? So depending on these types of distributions, we have one more thing, and that is called as density. Before that, I'll explain you the concept of density from very basic 7th standard. Okay. So let me recall the concept of density. If I take a piece of stone, let's say this is a stone, okay, and let's say this is a wood, a log of wood. Now we can see that log of wood is looking much bigger than the piece of stone. If I take this both and place it in water, I throw it in water, we know that the wooden log will float while this will sink. If I break the stone into two pieces, again the two pieces will sink. But the log, if I make two pieces, again they will float. So the question is, what is the difference? Looking here, the mass I can take it of 5 kg and I can take the mass of this as 2 kg. Even I can take it as 0.2 kg. Small, I am taking a small piece of stone or pebble and putting it in water, it will sink. So the mass is not a factor. If I look at the volume of this one is large compared to the volume of this one, which is very small, right? Still, volume is not a prominent factor. So what is important here is density. So what is density? Density we have learned as mass by volume, right? Now I am being very specific, more specific this time, because I am calling it as mass density, because we are dealing with mass. How mass is distributed in a given volume. Sir, how to imagine that? Imagine a classroom. Imagine the classroom in which you are attending the class in your school, and there are 50 students in your class. Great. Now keep the classroom as same, don't change anything, and put here 500 students. What will happen? So the volume is same, mass is changed, and the density increased, because the volume in which the people are packed is very high. And in such situations, the density increases. And in that case, the same thing happens for the log and the stone. The wooden log, what happened? When you break it into 1 million pieces, each piece will have those molecules which are loosely packed inside the given volume. But in this case of stone, They are very tightly packed in a given volume. That's why the density is very high. Now let's try to understand in mathematical way. If I look at the density of a log, let's say, so for the log, the density of log, let's say, I'm just making it as 5 by 10. So when the mass was 5 and the volume was 10 meter cube, the density is half. If I increased the mass to 500 and made here as 1000, again the density remained very low, 1 by 2. If I made it at 10,000, let's say, the mass, very heavy log, whole divided by the volume also automatically increased, 20,000. Still, the density remains same. So, density is a factor which remains constant for a given object. Understood? So, keep in mind this concept. Let me come back to our distributions. So, if we are dealing with linear charge distribution, one prominent factor which remains constant, and that is called as linear charge density. Now be very careful. Previously we discussed about mass density. Here it is charge density. So linear charge density will be denoted by lambda, and that is nothing but how the charge is distributed in a given length. So sir, you mean if I take a wire, what factor remains constant for this wire? Lambda. Charge will be different. Length will be different, so but it has a fixed length. Okay, so if I take this wire and if I cut this small part A, if I take this long part B, or if I take the remaining wire part C, A part is very small compared to B and C. The amount of charges present in A will be very less compared to B and C. Yes sir. The length of A part is very small compared to B and C, of course. But what is constant for this wire? Lambda. So, lambda of A will be equal to lambda of B will be equal to lambda of C. That's an important property of linear charge density. Similarly, if we call as surface charge density, what happens for surface charge density? If I take a sheet and if I take this small area, this huge area and this very big area, for each one, what remains same? A, sigma B and sigma C. Sir, what's sigma? Surface charge density is denoted by sigma, and that will be equal to what? Charge present in a given area. Okay. Similarly, if I go for the third case, that is volume charge density. The volume charge density is denoted by rho. Now be very careful, mass density is also denoted by rho. Okay, so don't get confused, and sigma is a parameter which is used in different contexts. So just don't generalize it that sigma always means charge density. No, later sigma in the third chapter we will make use of sigma as conductivity. Be very careful. So don't. There are only in physics, whole physics, there are few symbols there are fixed, like H, Planck's constant, which you have learned in chemistry also last year, C, speed of light, and universal gravitational constant, that is G. Other than this, all symbols are used randomly in different places. So don't get confused with that. No, just to no particular reason. Okay, there is no particular reason. Okay, so rho is given by, similarly we can make a relation for volume charge present in a given volume, that will be our volume charge density. Now, since we have for JE also, and a little bit our NCERT also focuses on this, so we will just make it as delta. Delta will make, so that later we will, when we integrate it or differentiate it, it becomes quite easy for us. So delta Q by delta L, delta Q by delta A, and delta Q by delta V. Because Q we assume, sir, why delta? Because Q we assume that the total charge, like in this sheet, if the total charge is Q, then for this part it will be delta Q, small part of section of delta Q is charge, and in that section the area is delta A. So these are the three relations, very important. Sir, what about units? Charge per unit length charge is coulombs, length is meter, so coulomb per meter. And here the charge is coulombs and area is meter square, so coulomb per meter square. And here it is Q is C and delta V is meter cube. We can find the dimensions. I'll not focus on dimensions this year a lot because dimensions is a part of 11th standard, but though they ask in board exams also, right? But what they ask mostly, those dimensions we will cover it. Okay, here you can make it yourself. Okay, coulombs is 80 and meter is length. Okay, so that we can see it. Okay, so here this is called as continuous charge distribution. A lot of continuous charge distribution parameters we will discuss in the, that's our remaining part of the chapter tomorrow. First, let's do some problems based on our these topics which we have discussed. Okay. Yeah, so the correct answer for this one is electric field lines can never cross each other. We have discussed why they can't cross each other. Let's see the next one. So electric field lines for a negative charge is radially inward. That's an important thing. Done. Let's see the next part. Question says a pair of 2q and minus q charge separated by a distance 2a can assume to be an electric dipole. No, we can't. Why we can't? Because one is 2q and one is minus q, right? Their magnitude should be equal and opposite, right? So the correct answer is no. It says the unit of electric dipole moment is Coulomb meter. So correct answer is option C, Coulomb meter. Newton per Coulomb is electric field, Coulomb is charge. So correct answer is C. Electric dipole moment is a vector quantity because I have specifically said that the direction is always from minus q to plus q. And that we have discussed in today's lecture also for equatorial plane. At the end, we put a negative sign because of this vector quantity. If it was not vector quantity, why we will consider the direction, right? So correct answer is vector quantity. The question says unit of electric dipole moment is dBi, dyne, Pascal and none. So this was a PYQ from CBSE once. dBi is another way of saying Coulomb meter. Okay, dBi was a scientist. In honor of him, dBi is a unit. Dyne is force and Pascal is pressure. Okay, so correct answer is option A, dBi. See. So question says over here, two charges 10 microcoulomb and another minus 10 microcoulomb are placed at 10 millimeter apart. The electric dipole moment of the set of charges. Now let me remind you the formula for electric dipole moment is P, that is equal to 2AQ. And let me just give you a small idea again that it is Q over here and it is minus Q over here and the separation itself we take it as 2A. So Q here is nothing but 10 microcoulomb. So we can just make it as 10 into 10 to the power minus 6. And the separation 2A, be careful, very common mistake students do. 2A itself is 10 millimeter. Don't multiply it with 2 again. So 10 into 10 to the power minus 3. So P will be simply 2AQ. That's our 10 into 10 to the power minus 3 into 10 to the power minus 10 into 10 to the power minus 6. 100 into 10 to the power minus 9 and that's 10 to the power minus 7. So correct answer is 10 to the power minus 7 Coulomb meter. That's our option B. Yeah, the question says direction of electric dipole moment is from negative to positive charge. That's the direction. So the electric field of an electric dipole is proportional to the distance as 1 by r cube. We have found this for axial as well as equatorial, right? For generally for a single charge, it's 1 by r square and 1 by r cube for dipole. So question says here a pair of two charges plus q and minus q separated by distance a will have its dipole moment. Now we know that dipole moment P is nothing but 2AQ. But the 2A is separation between q and minus q. But the question itself is saying the separation is A. So the correct answer for this will be AQ. Be very careful with this. Let's see. So two charges, one 5 nanocoulomb and another minus 5 nanocoulomb are placed 1 millimeter apart. The dipole moment will be how much? So first of all, let me write here Q is given as 5 nanocoulomb, 5 into 10 to the power minus 9 coulomb. And placed at R is equals to, or let me just make it as 2A instead of making new symbols. 2A is 1 millimeter apart, so 10 to the power minus 3. So we know that dipole moment formula is nothing but 2AQ. So 2A is 1 into 10 to the power minus 3 and Q is 5 into 10 to the power minus 9. So that will be 5 into 10 to the power minus 12 Coulomb meter. That's our option. Okay. Let's see the next one. The question says an electric, now be very careful, I have already explained you how to proceed a problem. What happens is majority of the students, they just read the question and then they think that how to proceed. First thing is, always when you read it, write the parameters, that will give you a direct hint. So question says an electric dipole held at 30 degrees, so theta must be 30 degrees. Straight away write it. If you will not write and just read the question, majority of times you know the things but you will not be able to solve it. So theta is 30 degree. With respect to a uniform electric field, E, which is equal to 10 to the power 4 Newton per Coulomb, great, experiences a torque. Tau is 5 into 10 to the power minus 8 Newton meter. And what they have asked, a dipole moment P. Now, V today itself, we have seen that torque tau is nothing but Pe sin theta. We know that. Let's plug in the values and P will be equals to tau by E sin theta. And tau is nothing but 5 into 10 to the power minus 8. E is nothing but 10 to the power 4. And sin 30 degree, that's half. We will put the values. So, 4 taking on the top, it will be 5 into 10 to the power minus 12. And sin 30 is half. So, let's take the 2 on the top. It will be 10 into 10 to the power minus 12. So, Coulomb meter, and that's our dipole moment P, which is option C.
Okay, so question over here says electric field due to an electric dipole on its axial plane is given by, so correct answer will be option B, that's we have already derived 1 by 4 pi epsilon naught, it should be epsilon naught, okay? 2 pi r upon r square minus a square whole square, okay? Without epsilon naught, like epsilon, there's a misprint here, it should be epsilon naught all over, okay? So 2 pi r upon 4 pi epsilon naught r square minus a square. Let me move to the next question. This question over here says electric field due to an electric dipole on its equatorial plane. Equatorial plane, we know it's minus p upon 4 pi epsilon naught. Again here it should be epsilon naught, epsilon naught, epsilon naught, and r square plus a square whole raised to 3 by 2. So it should be option C. Let's see the next one. An electric dipole consists of two opposite charges of magnitude this much. So let me just write here Q will be equals to 4 into 10 to the power minus 5 Coulomb and separated by a distance of 2 meters. So 2A itself is 2 meters. The dipole is placed in an external electric field. So electric field here E will be equals to 4 into 10 to the power 5 Newton per Coulomb. What will be the maximum torque? Now we know that torque tau is equals to Pe sin theta. But for maximum torque, theta is 90 degree, right? So torque tau will be equals to Pe. And dipole moment is nothing but 2aq into E. And 2a we already have here 2 meters, Q as 4 into 10 to the power minus 5, and electric field is 4 into 10 to the power plus 5. 4 4s are 16 2s are 32 Newton meter. That will be our correct answer. So option A, that's our correct answer. Let's see the next one. Over here says the torque experienced by the electric dipole having dipole vector given by, so dipole vector is given by P, and that is equals to how much? 2I minus 3J plus 4K, right? And placed in an electric field E, that is given by minus 3I plus 4J minus 2K. So torque tau, we know that it is equals to P cross E, cross product with E. So how do we find cross product? Let me just write here I, J, K, and let's write first the components of P, that will be 2 minus 3 4 minus 3 4 minus 2. So that will be torque tau equals to, let me just multiply using cross product. So when you are multiplying using cross product, right here I cap, ignore the row and the column of this, okay? So we left with 4 elements, and that is, yes, 6 minus 16 minus j cap into how much it will be, minus 4 and plus 12 plus k cap into 8 minus 9. So that will be minus 10 I cap minus 8 j cap and minus k cap. That will be our torque. And what's the unit? Newton meter. Option A. Let's see. So question over here says the torque experienced by the electric dipole having a dipole vector given by
P, which is equals to I cap minus 2j cap plus 3k cap, that's dipole vector, and placed in an electric field E, that is equals to minus 2I plus 5j cap and plus 3k cap. So torque tau will be equals to P cross E. So let's find the cross product, I cap, j cap, k cap, and P here is 1, minus 2, 3, E here is minus 2, 5 and 3. So this will be I cap into, torque here is I cap into 3 2s are minus 6 and minus 15 minus j cap into 3 and plus 6 plus k cap into 5 and minus how much, 4. So this will be minus 21 I cap minus 9 j cap and plus k cap. That's option C. Understood? Let's move to the next one. The torque experienced by an electric dipole will be maximum if the angle between the electric dipole moment and electric field is maximum, it's 90 degree. We have discussed in the theory part. Let's see the next one. So question over here says an electric dipole consists of two opposite charges of magnitude. So let me just write here Q, that will be equals to 3 into 10 to the power minus 5 Coulomb, separated by a distance. So 2A itself is 1 meter. The dipole is placed in a uniform external field of electric field E, that will be 4 into 10 to the power 8 Newton per Coulomb. The maximum torque experienced by the dipole. So torque tau, that will be equals to, for maximum theta is 90 degree, we know, so it will be PE. P here is 2AQ, so 2AQE, and 2A is nothing but 1, Q is nothing but 3 into 10 to the power minus 5, electric field E value is 4 into 10 to the power 8. So it will be how much? 4 3s are 12 and 10 minus, 8 minus 5, that's 3. So it's minus 3 here given, so correct option should be option D, none. Yes. So let's see the next one. What charge would be required to electrify a sphere of radius 25 centimeters? So let's imagine a sphere and the radius of the sphere is 25 centimeter over here. So as to get a surface charge density, so R, let me write here 25 into 10 to the power minus 2, that is our radius of the sphere. And so as to get a surface charge density, we know that it is denoted by sigma, that is nothing but 3 by pi Coulomb per meter square, that's a unit, standard unit of sigma. Now sigma is nothing but charge upon area, we know that from the previous lecture. So area here is nothing but 4 pi r square, that is the outer surface area of this sphere. So charge we are looking for, so Q will be equals to sigma into 4 pi r square. Let's put the values. Sigma over here is 3 by pi into 4 pi into r square, which is 25 into 10 to the power minus 2 whole square, which I can write it as 25 into 25 into 10 raised to minus 2. Now we can cancel pi with pi straight away, and here we left with 4 into 25, that's 100, right? So 4 into 25 is 100 and 100 into 10 to the power minus 2, all these gets cancelled. We left with 3 into 25, which is 75 into 10 raised to minus 2, and that is nothing but 0.75 Coulomb. That's our correct answer. Let's see the next one. Let's start with this problem. The question says over here, a charged spherical conductor has a surface charge density. Let me write here as sigma, that is equals to 0.7 Coulomb per meter square. When its charge is increased by, now be very careful because the word by is very important here. Sometimes they can write it as when its charge is increased to. So it will have a different meaning. If it is saying increased by, which means the new charge value will be higher than the previous one, right? Yeah. So it is saying when it is increased, let's say the previously charge was Q. Now the charge is Q dash, and that will be equals to Q plus 0.44 Coulomb. Okay. This is called increased by. Sir, what if it was increased to? Then you will not write Q plus this thing. You will straight away write 0.44. Okay. The charge density changes by, again the word is changes by. Changes by means again the sigma dash will be equal to sigma plus 0.14, and sigma is nothing but 0.7. So let me add straight away 0.14 and it will make it 0.84. That will be its new surface charge density. Find the radius of the sphere and the initial charge. So let's assume that sphere is having radius r, that will remain same in the previous case as well as this case, right? Because only the charges and sigma is changing. So in the previous case, sigma will be equals to q upon 4 pi r square. That will be our first equation. Now when the charge is increased, it will be sigma dash, that will be equal to q dash upon 4 pi r square. Still it is the same, r is same. Now let's divide sigma 1 and sigma 2, or equation 1 and equation 2. It will be sigma over sigma dash, that will be equal to q upon q dash. I hope this is clear. Now this implies sigma, that is 0.7, sigma dash, that is 0.84, q is q, and q dash is q plus 0.44. Correct? Now we can do one thing, we can cross multiply, and before we do that, let me just simplify here. Let me remove this point, the decimal, and this will give us 70 over 84, that will be equals to q over q plus 0.44. Let's cross multiply. So let me do it over here. It will be 70q plus, let me multiply 70 with 0.44, and that will give us 30.8. That will be equals to 84q. Any doubt? So 30.8 will be equals to 84 minus 70. That will be how much? It will be 14q. So q will be equals to nothing but 30.8 divided by 14, and that's our 2.2 Coulomb. That's our charge on the sphere. Initial charge on the sphere is 2.2 Coulomb. Now if this is the charge, let's put it in back in equation 1. So from equation 1, r square is nothing but q over 4 pi sigma, right? And that will be, q is how much? 2.2 over 4 into pi, let's put it 3.14, and sigma is 0.7. This is r square, right? So let's simplify it. 4 into 3.14 into 0, or let's make it as 22 by 7. That would be better option. Yeah, so that will be 22 by 7. And let's remove this point, and it will become here into 10. Let's remove this, and you will get here 10. 10 and 10 gets cancelled. 7 and 7 gets cancelled, and this will get. So r will be 1 by 2, because 1 by 4 root is 1 by 2, that's 0.5 meter. That's our radius of the sphere, and that's our charge, 2.2. Any doubt? Let's see the next one. Okay, so question over here says 64 drops of radius 0.02 meter and each carrying of 5 microcoulomb are combined to form a bigger drop. Find how the surface density of electrification will change if no charge is lost. Okay, so first of all, let's find what will be the relation between the radii of the bigger one and the smaller one. So if let's imagine that such small 64 drops are combined together to form such a big drop, then volume of the smaller drop will be 4 by 3 pi r cube, right? If I multiply it with 64, this must give us the volume of the bigger drop, 4 by 3 pi capital R cube. Let's cancel out pi and pi both the sides. So r cube will be equals to 64, r cube into 64, that will be equal to capital R cube. And that will be 4r, that will be equals to capital R. That's our equation number 1. That gives us relation between the radii of the smaller drop and the radii of the capital drop, right? Now, if this is the situation, let's see what is the sigma. Sigma for the smaller drop, let me call it as sigma. That will be equals to the total charge q upon 4 pi small r square. That's our first one. And sigma dash, that will be our total charge on this larger drop. That will be q dash. It won't be q because there are 64 such q's upon 4 pi capital R square. That is equation 2. Now let's divide sigma and sigma dash, that is equation 1 and equation 2. So sigma over sigma dash, that will be equals to capital R square over small r square, and q over q dash. I hope this is clear, right? Now capital R is nothing but small 4r. So let's substitute the value sigma over sigma dash, that will be 4 4s are 16 r square whole divided by r square into the total q is given as 5 into 10 to the power minus 6. That's the charge on a single drop, but there are 64 such drops, so q dash will be 64 into 5 into 10 raised to minus 6. Let's cancel out r square with r square, 10 to the power minus 6, 10 to the power minus 6, 5 and 5. 16 4s are 64, so sigma upon sigma dash is 1 by 4. That's the ratio in which the charge densities will alter. Let's see the next one. So in the last lecture we discussed about continuous charge distribution. Let's move to another topic, a small topic we will discuss, and the role of this topic will be very crucial in our next part, which is the last part of this chapter. So let me write here, this is known as electric flux. Now 90% times the students, they understand this electric flux wrong in school. Why they understand it wrong, we will see that within a minute. So let me just write the definition of electric flux. So electric flux is nothing but, you can define it as, it can be defined as the bunch of electric field lines passing through a given area. So pay attention now. If there are field lines which are going or passing through any charge, let's take a random example. I'm just taking as plus q, you can take it minus q also, doesn't make any difference. So let's say these are field lines. I'm just randomly making some field lines here, so that they don't touch each other, but these are the field lines which are coming out of this charge and they are going away from the charge. So let me just draw a few so that you get a slight idea of what is flux. So these are field lines which are coming out of this particular plus q charge. Okay. Let me just draw it like this. Let's make it like this. Okay. So they are emerging out from the charge only, but okay. So let's assume these are our field lines which are going radially outward due to the positive charge. You can see here that the field lines are very dense around the charge, right? And if they are very dense around the charge, which means the field is stronger in this region compared to the field which is in this region. So as this is obvious because we know the value from mathematical relation, E is equals to kq by r square. As the r, the separation increases as we go away from the charge, the electric field decreases, right? Now here if you take a small area, now be very careful, I am not dealing it in 2 dimensions, I am dealing it in 3D, okay? So don't just take it like as you can see it on the board in the classroom or the screen here, okay? It's a 2D, but in reality the field lines are going in 3D, in all possible 3 dimensions. If I imagine a small area like this, okay? So just to make it more specific, let me just draw it like this, okay? Okay, this is our area, and if I make the similar kind of area in this region, and ideally you can see that they look quite, just assuming that they both are equal in size, right? Yeah. So if you look at the area A and if you look at the area B, let's count the field lines passing through A. 1, 2, 3, 4, 5. Okay, 5 field lines are passing through A. Number of field lines passing through B, though they are both are equal in area. Okay, so the field lines passing through B is only 2. So the field lines passing through a given area will determine the intensity of the field. That will decide that how much stronger the electric field will be. right? So these bunch of field lines passing through a given area will be defined as flux. Very crucial, important point. Okay, if you know the flux, you know the field. If you know the field, you can find the force, right? So this is very important part. So flux is bunch of field lines passing through a given area. Yeah. B, exactly. So flux at A will be higher than flux at B, and mathematically it is given by a symbol like this. It is phi. Why we are using phi? No sense of this question. It's just a symbol, right? So flux phi is nothing but electric field E dot area. Area, be very careful here with the area, E dot A, and when you remove this, you get n cap. N cap is normal to the vector. What is the use of this? I will explain. Okay. And when you remove this dot product, you simply get EA cos theta. That's our electric field. Okay. And when you are using integration, we will make use of E dot ds integration. That will be our phi. Okay. So these are the three common used relation in case of flux. Okay. Now, what is the role of n cap? What is the role of cos theta? We will see within a minute. Okay. Okay, let's see what is the role of cos theta and n. Now try to understand it very carefully, because they will use these concepts, and this will be repeated again in chapter 5 or 6. Okay, so see what is happening. Let's imagine a Captain America shield. Okay, you have seen Captain America shield? Yeah. Okay, now because it's a 3D, so you have to be very careful about that thing. Okay. Now somebody is firing bullets, right, in this direction. Okay, obviously you will keep the Captain America shield like this, so that all bullets will go and stuck on the shield and you will be safe here. Now what happens if somebody is firing the bullets from this direction? So that is obvious that you will be killed, right? If you are keeping the shield in this same position. Sir, what happens if they are firing from the top? You have to keep the shield like this, right? So be very careful, understand the core concept. What is happening here is, what is the direction of electric field? So direction of electric field is this side. What is the direction? How the area is placed? So the area is placed like this. Where will be the normal to this area? So normal to the area will be, you can point it in this direction or you can point it in this direction. These both are normal. We call it as perpendicular to this area, right? So if I am assuming if the normal is in this direction, ideally speaking, if this is the normal and the direction of electric field is also in this direction, what is the angle between the normal to the area and the electric field? Theta is 0 degree. 0 degree. Be very careful. I am repeating again. Be very careful. Okay. There are two words. I will write it in statement. Put it in your notebook. Okay. One is normal to the area. Normal to the area. Another word is area. Okay. So normal to the area and electric field, theta is 0 degree. But angle between, this is, okay, so I am writing in this case, or you can draw this diagram also in your notebook so that later reference, or anyways, I'll post this on the YouTube, okay, so you can watch it again. Very crucial part. So theta is 0 degree in case if you are finding the angle between normal to the area and electric field. Okay, and electric field vector. Theta is 90 degree in this case between area and electric field vector. Sir, how? See here, I am drawing a diagram. Again, electric field is this and it is making 90 degree with the exactly area of the shield. It is making 90 degree, but the angle between the normal to the area and electric field, they are parallel. Look at these two black lines. Now what if somebody is firing bullets from the top? Now from the top, look at this. If this is the field direction going downward and you are still keeping the shield like this, the angle between the field and the shield is 0 degree in this case. But normal, sir, normal will still remain here only. So look at this angle. Now in the second case it is 90 degree. Clear it is? Second case you didn't understand. So let's do one thing. Let's reshare the screen. Okay. Next, can you see it? there is a shield like this. Okay, I want to explain you from 3D. Look at this 3D. Can you see the 3 dimension all around, right? Okay, now pay attention now. Let's recall our concept. Okay, so if, one second, let me just add here pen. Yeah, let's say somebody is firing bullets from this side. I'll show you all the whole view. Now if somebody is firing bullet from this side, look at the front view. Can you see it? Okay, coming back to this situation. Can you see the field lines? The field lines are going like that. Now if I extend this field line, okay, if I extend this field line will go from here and make what angle with the area? Tell me. Exactly. Now if I want to make a perpendicular to the area, look at this perpendicular to the area. Is it the perpendicular to the area? Yes. Sir, make a 90 degree here. This is 90 degree, right? Now, what's the angle between electric field and perpendicular to the area? Zero. Both are pointing in the same direction. Look at this. Yeah, 0 degree, right? And when it is 0 degree, between what? Between the normal and cap and electric field, the angle is how much? 0 degree. And in this case, maximum flux will pass through this shield, right? Theta here is 0 degree. So cos 0 is 1, right? So flux phi is E dot A. Now what happens if somebody is firing bullet like this, instead of firing like this, if somebody is firing bullet like this? Sir, in this case, you should keep the sheet like this, right? Yeah, you should keep it like this. But let's suppose if you are not keeping it like this. So let me just remove this part. You should keep like this shield to save yourself, right? Okay, one second. It's okay. You should keep the shield like this, right? But you are not keeping like that. You just keep the shield like this. Now what happens? Let's see this. Let's see the top view. Now bullets are coming like this, and still the shield is like that. This is our electric field vector from the top. It is going like that, right? What's the angle between? Straight down, right? If it is going straight down, and what? Oh yeah, exactly. So electric field and the area is 0 degree here between electric field and the area, because you can't see the shield. It's parallel. It's completely parallel. Okay, but look at the normal. Normal is this one. Yeah. So between the normal and the electric field, what's the angle? Yeah, 90 it is. Let me just see it again in the same way. So theta is what? 9. Between the normal and the electric field, the angle is 90 degree. And if it is 90 degree, then the flux is 0 in this case, which will pass through the area. So in the first situation, the flux will be maximum. The flux will be maximum in this case, first case, but in the second case, the flux will be 0. Why 0? Let me repeat again. Angle you always take. Angle is measured between whom? Normal to the area and electric field. Always never look at the angle between electric field and area. Always look at the angle between normal to the area and electric field. Okay, sir, do one thing. Just make a switch. Let's say this is our notebook, and let's remake it as 0 degree, just 0 like this. 0 degree I made it. Okay. Do you still have your normal at the same place? Now where will be the normal? It will be going vertically upward in this case. This is the new normal. So let me write it as N2. Because these will be the normals perpendicular to the surface, right? And where is the electric field this time? So still electric field is like this. What is the angle between? Yeah, what's the angle between electric field and normal this time? So 90 degree. And if it is 90, cos 90 is 0. So now the flux will not pass through the area. You can see that it's not passing and hitting the area. Yeah. Okay. So previous case. Yeah.
Yeah, electric field lines are case 1 only I am taking. Case 1 only I am taking. 90 degree. Yeah, perpendicular to the normal. That's why the flux will be not passing through the area. You can see that. Okay. 0. Yeah, so electric field and area becomes parallel to each other, flux becomes 0. If I slightly change the angle, look at this, I am changing the angle. As the angle is changing, the shield will stop more and more bullets. And if the shield is at perfectly 0 degree, no bullets are stopped, right? If I am standing over here, I will be killed in this situation, right? But if I am keeping the shield, if I slowly increase, the more and more bullets will stop. Now, when you are saying the bullets are stopping here in this case, you simply mean that flux are passing through the area. Understood the concept? This is very important for this chapter as well as because this is, I have found 99% students, they understand it wrong and they get confused with the angle. So just the statement which I have written, though I don't know at what angle, yeah, here angle, this is so perfect. The angle is always measured between the normal to the area and electric field. Yeah, now it makes more sense of how the theta is. So all this is very crucial. Try to write it. This is very important part. Theta is normal. Angle between normal to the area and electric field is always considered when you are finding the flux. And we have 3 formulas for flux. We will do tomorrow problems on this. And E dot ds integration, E dot A dot product, and directly if the theta is given. So this is obvious that you will find a function in any problem. You use this one, integral. When you find 2 vectors, you use this straight away. And when you find an angle, you use the third one, right? But angle is always measured between normal to the area and electric field. And to confuse you, they will give you the angle between area and electric field. So the question over here says, if E equal to 6I plus 3J plus 4K, that's our electric field vector. Calculate the electric flux through a surface area of 20 units in YZ plane. If there is a plane which is YZ, let's suppose this is our YZ plane, Y axis and Z axis, then the perpendicular to YZ plane, we know the normal to this plane is X plane, X axis, right? So we will say that area vector, the normal to the area will be 20I cap, right? So we can find the flux phi, that will be equals to E dot A, and unit vector which is area. Be very careful, area is a scalar quantity, but here this I cap denotes the normal, right? We have done that in the previous lecture. So E will be simply 6I plus 3J plus 4K multiplied with 20 I cap. So if you multiply, we know that I dot I, it will be 120, and flux is a scalar quantity, and the unit will be electric field as a unit of Newton per Coulomb, and area is meter square. So it will be Newton per Coulomb meter square. Okay. So the question over here says, if E is equals to 8I plus 4J plus 3K, calculate the electric flux through the surface area 100 units in XY plane. So if it is XY plane, so this plane is X and this is that's a X axis, and this direction is Y axis, right? So perpendicular to XY is Z axis. So the normal will have a K cap, right? So we can write here area vector. Be very careful. Area vector here will be 100, and K cap denotes here the normal vector, normal to the area. So our flux phi will be equals to E dot A, and that will be equals to 8I plus 4J plus 3K multiplied with area vector, that will be equals to 100 K cap. So that will give us how much? 300 Newton per Coulomb meter square. That's our unit. Okay. We'll move to the next one. So question over here says the electric field. Let me write the electric field here. E, which is equals to 5I plus 4J minus 4K. Let me keep it in a bracket into 10 to the power 5 Newton per Coulomb, and the area here again given in terms of vector, that is 2I minus J cap into 10 to the power minus 2. Again I am repeating, this is our area is the normal. So if it is in normal case, phi will be equals to the dot product of E dot A. So here it will be 5I plus 4J minus 4K multiplied with
2i minus j multiplied with into 10 to the power 5, and I am just keeping the powers together, right? So now let's do the dot product. So 2i into 5, 10, and j with j minus 4, and multiplying 10 to the power 5 into 10 to the power minus 2, 10 to the power plus 3, and that will be equals to 6 into 10 to the power 3 Newton meter square per Coulomb. That will be our unit. So that's answer is 6000 Newton meter square per Coulomb. So the question over here says a circular plane sheet of radius 10 centimeter. So r is nothing but 10 centimeter. So we can just simply write it as 10 to the power minus 2 meter, right? It is placed in a uniform electric field. So our electric field E is nothing but 5 into 10 to the power 5 Newton per Coulomb, making an angle theta as 60 degree with the field, right? Question says calculate electric flux through the sheet. So if we try to draw this is our circular plane sheet, and the electric field is making, let's say the electric field is making here, this is our E, making an angle of 60 degree with the sheet, right? But we don't need this angle. What we need is our angle must be between electric field and normal to the circular sheet. So this is our n cap, and if this is 60 degree, this will be 30 degree. That is obvious. Why? Because the normal is 90 degree to the sheet, right? So that is 30 degree, and so let's use the formula. Flux phi will be equals to EA cos theta, correct? So E is nothing but 5 into 10 to the power 5. Area is pi r square. So we will write it as 22 by 7 into r square, which is 10 into 10 to the power minus 2 into 10 into 10 to the power minus 2 into cos 30 degree. So cos 30 is nothing but root 3 by 2, right? So what we will do here is let's multiply them. So let's multiply the powers first. 10 to the power 5 and 10 to the power 6, and 10 to the power 6 and 10 to the power minus 2 and minus 2 4. So 10 to the power 2 we left with, right? And let's multiply 5 into 22 by 7. So that will be 15.714. Well, let me repeat again. 10 to the power 5 and 10 to the power 6, 10 to the power 6 minus 2, 10 to the power 4, and minus 2 is no, it's fine. Exactly, yes. It should be 10 into 10 to the power minus 2, correct? So 10 into 10 to the power minus 2, that's a small error. So here if you make this, that will be 10 to the power 3, and cos 30 is root 3 by 2, right? So let's multiply this value. Root 3 is, I am taking 1.7, so that will be 26.7 divided by 2, that will be approximately 13.35 or 36, let's make it 10 to the power 3 Newton meter square per Coulomb. That's our answer. Any doubt? We'll move to the next one. Question over here says consider a uniform electric field. So let me just write here electric field E, that will be equal to how much? 3 into 10 to the power 3 I cap, right? Which means it is along x-axis, Newton per Coulomb. Calculate the flux of this field through a square. Square it is given. So area, directly area is given. So it is 10 centimeter square. Let me convert it into meter square. 10 into 10 to the power minus 4 meter square, right? Now this is the data given. The first part, it says it's plane. The plane of the square is parallel to YZ, which means our normal will be along x-axis, right? So our area vector, we can make it as 10 into 10 to the power minus 4 I cap, right? Sir, what if it was not along x-axis? Straight away 0, because if the normal is not along x-axis, straight away the flux will be 0. So we can find flux phi, that will be equals to E dot A. So that will be 3 into 10 to the power 3 I cap into 10 into 10 to the power minus 4 I cap. Dot product straight away, that will give us how much? 30 into 10 to the power minus 4 and 3, that's minus 1. And that will be 3 Newton meter square per Coulomb, right? And now that's our first part. Second part, be very careful. It says the normal to its plane. Normal to its plane. Normal to its plane means, let's assume that this is our normal to its plane, right? N cap is making 60 degree with the x-axis. Okay. That's fine. That's fine. We are not focusing on that. I'm just finding the direction first. So N cap Yeah, that's centimeter square, no? So centimeter square, if you convert, it is meter square. See, 1 centimeter is 10 to the power minus 2 meter, right? So 1 centimeter square, that will be 10 to the power minus 4 meter square, no? Squaring both the sides, right? Okay, let me come back to the second one. Understood the first part? Yeah. So the second one, the normal to its plane. So if this is the normal, it makes 60 degree with the x-axis. So let's say this is our x-axis. So along x-axis, it is making 60 degree, right? And we are given directly that our electric field is also along x-axis. Look at this I cap. So angle between which we are taking electric field and the normal, right? So theta is straight away will be here 60 degree. Be very careful. It won't be 30 degree in this case, right? So flux phi will be equals to EA cos 60 degree. In this case, second part, E into A, we already found it in the first part, which is 3, and cos 60 is 1 by 2. So in that case, it will be 1.5 Newton meter square per Coulomb. Any doubt? Let's see the problem. The question over here says, given a uniform electric field. Now, electric field E is given over here as 5 into 10 to the power 3 I cap. I cap is our x-axis, right? And find the flux of this field through a square of side is given here. So side length L is 10 centimeter. Let's put it here as 10 into 10 to the power minus 2 meters. So let's calculate area over here only. So area will be square of this L square. So that will be how much? 100 into 10 to the power minus 4 meter square, right? On a side whose plane is parallel to YZ. So let's assume that it is parallel to YZ like this. This is our parallel to YZ. So this is our y-axis, and let's call it as z-axis over here, yz. So perpendicular will be where? It will be along x-axis, right? Okay. What would be the flux through the same square if the plane makes 30 degree? Read the question very carefully. The plane is making 30 degree with the x-axis. So if the plane is making 30 degree with the x-axis, the normal will make how much? 60 degree, right? Because we always take the angle between normal and the x-axis, right? Normal and the field, sorry. So field is along x-axis. So theta will be 60 degree here. So flux phi will be equal to EA cos 60 degree, right? So electric field over here will be how much? 5 into 10 to the power 3. Since it is along I cap, so area I am just keeping it along I cap only, 10 to the power minus 4 into cos 60, which is half. So let's make it as 500 into 10 to the power minus 1 whole divided by 2. So that is 250 into 10 to the power minus 1, and that is how much? 25 Newton meter square per Coulomb. Theta is very confusing because you are not reading the line properly, and it will confuse because it confuses everyone. So be very careful. You have to read it at least 2 or 3 times, and just keep in mind that one thing, we always find the angle between normal and the electric field, not between electric field and the area. Yes, so whenever you read the question, just recall this concept that you are looking for angle between normal and the electric field. And read again the question and see if it is given. Like in this case, it is clearly saying that flux through the same square if the plane makes an angle 30 degree, not the normal to the plane makes an angle of 30 degree. If instead of plane, if they say normal to the plane makes an angle of 30 degree with the x-axis, then it's fine. Okay, straight away that angle. Understood? Okay, so let's see the last part of this chapter, that is our Gauss law. Okay, so let me just write here Gauss law. Very important part because that one derivation might come from this part. Either they will give you the question from dipole, the derivation, equatorial or axial plane, or the derivation will be from Gauss law. Let's understand what is Gauss law. So let me write the definition of Gauss law. Very important, don't make any change in this particular definition. Okay. So according to Gauss's law, according to the Gauss's law, the total electric flux coming out from a closed, I'll explain each and every word, okay? So keep patience, just write the definition first. From a closed Gaussian surface will be equal to 1 over epsilon naught times the total charge enclosed by the surface. Very, very important for our numerical problem, as well as the two or three derivations which are related to Gauss law. Now let's focus on the statement, what this statement says. Very simple and very important it is. Gauss's law says that the total flux, this is another way of counting flux. What was the first method? We have already discussed in the previous lecture. Phi was equals to E dot A n cap dot product, or you can simply, if you are given with the formula, E A cos theta, or the third way we found it as integral of E dot dA, that we will use here to derive some expressions, right? So these three methods we have already discussed. Electric flux. Another and simple yet very powerful way of finding electric flux is Gauss's law. So according to this law, the total electric flux coming out from any closed Gaussian surface. Now as a beginner from 12th standard, many means mostly 99% people, they have a problem with this word, Gaussian surface. Sir, what is a Gaussian surface? How you define a Gaussian surface? Is there a way we can define a Gaussian surface? We'll talk about that thing. It's always equal to 1 by epsilon naught times the total charge enclosed by the surface. Now first thing, to be a Gaussian surface, it should be closed. So closed can be like this, yeah, enclosing the charge. Can this be a Gaussian surface? No, because it's an open surface, right? So Gaussian surface, it should be closed, first thing, and it can be any random surface, but from 12th standard you have only three types of Gaussian surface which we will consider. First will be spherical surface, second will be cylindrical surface, and the third one will be cubical mostly. We will not talk about any other random surface, okay, because we are dealing 12th standard only symmetrical surfaces, right? So if you imagine some charge plus q, minus q, 2q, 8q, any random set of charges, you can imagine a surface around it that is purely spherical, okay. So when to imagine cylindrical and cubical, that is also very rare. We will see how those situations, okay. So any surface that encloses and it is closed surface is known as Gaussian surface. So don't think much about Gaussian surface. They are just mostly spherical, and rarely we will think of cylindrical or cubical, okay. And how do we express this Gauss's law in mathematical form? It is given by flux phi will be equals to total charge q enclosed. I am writing the specific word En. This is very crucial while dealing with the numericals. So mostly people, they remember this as q by epsilon naught, but it should be q enclosed by epsilon naught. That is our flux. So from where this expression arrives, we will derive it. We will find the proof of this Gauss's law within a minute. So any doubt up till here? So let's see how we got this expression. So proof of Gauss's law. Let me write here, proof of Gauss's law. So let's imagine that, yeah. Can you repeat your question? See, sometimes the question, they can give you a simple question for 1 mark, define Gauss's law. In that case, you have to simply write this definition which I have given you and write this particular mathematical relation, right? But if they give you the same question for 2 marks or 1.5 marks, sometimes you have to give the proof also, because proof is not that large. It's a hardly 2-3 steps, right? So if they are giving you in higher weightage question, you have to give the proof. If they give you in hardly 1 mark definition, then you don't have to do the proof, okay? So let's see what is the proof according to Gauss's law. Let's see, plus q. Let's assume a charge plus q. And if you imagine the field lines, they are going radially outward and they are around, we can imagine a Gaussian surface, a closed surface which encloses this charge, right? So if the field lines are going radially outward like this, okay, around this charge, all over here, then we can imagine a small area, a very small area, and see how many field lines are passing through this area outward, okay. So this flux phi, we know that it is equal to E dot area, right? Let's put an integration E dot dA, that will be the total flux coming out of this, right? Now electric field at any point away from this charge at a distance r, we know that we have learnt it in the previous lectures, 1 by 4 pi epsilon naught q upon r square, right? Integration of dA. And integration of dA gives us, that you will learn it in maths 12th standard chapter 8 application of integrals. So for the time being, just remember that sir is going absolutely correct. Okay, so integration of dA will give us, let me just take the constants out, 4 pi epsilon naught r square, and integration of dA from maths will give us the total surface area, the outer surface area of this sphere, and that is nothing but how much? 4 pi r square. So this, from where this arrives? Maths, integration. So there you will understand how integration of a sphere area will give you 4 pi r square, and if you are dealing with a circle, it will be pi r square. Be very careful, there is a difference between sphere and circle. So don't get confused between that. So flux phi will be this. Let's cancel out 4 pi with 4 pi and r square with r square. We got our flux phi as q, which is enclosed in this surface, upon epsilon naught. So this is our proof of Gauss's law. Yeah, this is small. That's why I said if they'll ask you question for 1.5 or 2 marks, simply add the proof so that you get complete marks. Okay. Many students, they simply write the definition, but definition is only for 1 mark. Okay. Then I'll move to the next one. Okay. Now, depending on Gauss's law. Now the question is, sir, what is the use of Gauss's law, so that you can understand the application better? See, starting from the very beginning, I have told you the chapter is based on 2 types of charges, positive and negative. Then I discussed about Coulomb's law. But I also discussed what are the limitations, where the problem arrives, though it's not, we can figure out, but the problem is Coulomb's law at a time takes 2 charges. Then we found the concept of field. And then we discussed how we can find the field for a dipole or on equatorial or axial plane. But to find field, you should know flux, because flux is E dot A. So if you can somehow find the flux, you can easily find the field. So Gauss's law basically focuses on finding the field. Okay, so because if you know the field at a point, you can easily figure out the force at that point. Okay, so there are different applications. Let me write the first application. The first application is field due to an infinitely long, straight, uniformly charged wire. Uniformly charged wire. So let's say if I assume a wire, straight wire, okay, and this wire is completely charged, let's say. So let me make it so that I can show the charges. Okay. Okay. 1 second. Let me just redraw it. Okay. So let's say the charge on this wire is positive, all over, positive, positive, positive. Sir, can we think of negative? Exactly, you can think of negative also, doesn't make any difference, you'll get the same thing. Sir, but it is saying infinitely long wire. So wire is very large, okay? And if you think of a spherical Gaussian surface, it will not be able to enclose it, right? So here we are forced to think of a cylindrical Gaussian surface. So let's say this is our cylinder, okay? Let's say this is our cylindrical Gaussian surface, okay? And we are finding the flux due to, okay, the cylindrical Gaussian surface. And the electric field due to this wire will be radially outward in all the direction, right? Yeah, radially outward because of positive. Let's assume that Gaussian surface here is having a position R, right? Sir, can you imagine a bigger Gaussian surface? Yes, you can. Sir, how you decide which size you can? See, if you are looking for electric field at a point, let's say this point. So you have to decide your Gaussian surface according to that, right? So large, if you are looking for electric field at this point, you can imagine a Gaussian surface of this size, correct? Okay, so the flux is coming out from the curved surface area of the cylinder, because here this is perpendicular, right? So no flux. Theta will not contribute here. The flux will not be contributing here. So we can say that flux phi, here, one second. Flux, one second, it's reloading. Just give me, okay. So we can imagine here flux phi, that will be equals to how much? E dot A. Any doubt in this part? Because we know this from previous lecture, flux phi is E dot A, correct? Now, we know that if we integrate this area will give us curved surface area of the cylinder. So R is radius, and let's assume that L is the length of the cylindrical Gaussian surface. So flux phi will be nothing but E dot 2 pi RL. Any doubt in this part? Flux phi from Gauss's law. We know that from Gauss's law, flux phi will be total charge enclosed Q in upon epsilon naught. Now what is Q in? So Q in will be the charges which are in this section of this cylindrical Gaussian surface, right? So be very careful. We will talk about that thing within a minute. So E into 2 pi RL. But sir, how much is the charge present in this section of the Gaussian surface? For that, let me remind you a concept we learned in the previous lecture, that is lambda. What is lambda? Linear charge density, and that gives us Q by epsilon naught. Q by L, sorry. So what is Q? Q is the charge enclosed in that small section. So length we are taking this L, not the complete length of the wire. L is that section of the wire. So Q will, yes, so Q in will be lambda into L. So let's substitute here lambda into L upon epsilon naught. That will be equals to E into 2 pi RL. Any doubt in this part? Let's cancel L with L. So electric field E, that will be equals to lambda by 2 pi R epsilon naught. Any doubt? Very important for problems. Direct question they ask in board exams. Okay, so in the previous lecture we discussed about electric field due to an infinitely long straight wire, and that was our first application of Gauss law, right? Now let's see, there are two more applications of Gauss law. So let's move to our next application. The next application is due to a sheet. So let me write here electric field due to a uniformly charged infinite plane sheet, somewhat like the paper sheet, okay, of your notebook. So if you imagine a sheet somewhat like this is our sheet, okay, then we know there are three sections for this sheet. One is behind the sheet, another is on the sheet, and third is in front of the sheet, right? And imagine that there is positive charge on the sheet. We can imagine a positive charge on the sheet over here. Now, if you imagine flux or electric field, it is radially outward. So let's say there is a small section of this sheet due to which electric field is coming out. So we can imagine a Gaussian surface somewhat like this, outward, radially outward, pointing in this direction. And there is another part of this field that will be radially outward in this direction, right? So electric field will exist only in region 1 and region 3. There is no electric field on the sheet, so E2 will be equals to 0. Electric field in region 1 must be equal to electric field in region 3 because it is uniformly charged, right? So we can say that E1 equal to E3, and that is equals to E. So from our basic idea of flux which we have discussed, our total flux phi, that will be equals to E1 plus E3, that our net electric field E1 plus E3 into the area of that part. and E1 plus E3 will give us E plus E, which is twice of E into area, that is flux phi. Now area of that small part. Now phi from Gauss's law, it is nothing but total charge enclosed upon epsilon naught, and that is equals to twice of E into A. Now we know that if it is a charge sheet, then sigma is nothing but the surface charge density, that must be equal to total charge enclosed upon the area of that part. So the charge enclosed by that area will be equals to sigma into A. Let's substitute this in place of Gauss's law. So sigma A upon epsilon naught, that must be equal to twice of E into A. Let's cancel out A with A, and we left with E, which is equals to sigma by 2 epsilon naught. Be very careful, we will use this expression in the next chapter. This is electric field, let me write here, electric field due to the sheet, electric field due to the sheet on one side of the sheet. Be very careful, it is on one side. Both the sides it will be sigma by epsilon naught. So one side of the sheet. So this is our second application of Gauss law. You can copy it. Because only 3 applications you have, so you have to just remember these Gaussian surfaces. Okay. So no other random they will not give you. Don't worry about that thing. Let's see the last application of Gauss law. So our last application of Gauss law is electric field. Be very careful, using Gauss law we are just finding field. So electric field due to a uniformly charged thin spherical shell. Okay. So if you imagine a spherical shell here, okay, this is our spherical shell. So in this spherical shell, the charge is present on the outer boundary of the shell. What is a shell? Something which is empty inside, like a football. Only the outer covering is there. And on this outer covering, we have positive charge. Okay. And field due to this will be radially outward because it's a positive charge. And let's assume that the radius of this is capital R. If we are looking for electric field at any random point, let's say we are finding the electric field at this point, any point this, which is point P, and this point P is at a distance of small r from the midpoint, the center of this shell. Then we can imagine a Gaussian surface all around like this. Okay, so this Gaussian surface we can imagine. Now we know that flux phi is nothing but E into area, electric field into area of the Gaussian surface. Now what is the area of Gaussian surface in this case? 4 pi r square. Any doubt in this part? Now from Gauss's law, phi is nothing but the charge enclosed by this Gaussian surface upon epsilon naught, and that is equals to E into 4 pi r square. Any doubt? Now here be very careful, though it's a 3D, but here the charges are present only on the outer surface. So sigma will be equals to Q in enclosed upon area. And here where is the charge distributed? So the charge is distributed along the area Q in upon 4 pi capital R square. Be very careful. So if we cross multiply, Q enclosed will be equals to sigma into 4 pi r square. This is our equation 1 and this is our equation 2. Let's substitute equation 2 in equation 1. So Q enclosed will be sigma into 4 pi r square whole divided by epsilon naught, and that will be nothing but E into 4 pi small r square. Let's cancel out both the sides 4 pi. and what we left with is sigma upon epsilon naught into capital R square upon small r square. That's our electric field at that point due to the shell. Any doubt? Now, this is outside the shell. Let's go into on the shell. Second case, yeah. On the shell. On the shell. Now, on the shell, small r will be equal to capital R. So, the electric field, straight away we can write it as sigma by epsilon naught, because r square and r square gets cancelled. Third case, inside the shell. Inside the shell. So, it will be 0. The electric field inside the shell will be 0. So, why it is 0? Because if we imagine a Gaussian surface inside, there is no charge enclosed by the, so no charge enclosed by the Gaussian surface. So, hence the electric field will be 0. So, I can write Q enclosed will be 0 inside the shell. So, here this first chapter gets over. And let's do a few problems based on this thing. Let's see. The question over here says the figure shows three charges 2q, minus q and 3q. Two charges 2q and minus q are enclosed within a surface S. What is the electric flux due to this configuration? Now be very careful, flux is a scalar quantity. So you have to take the negative sign of the charges, right? So that flux we know from Gauss's law is flux phi, that will be equals to the total charge enclosed by the surface upon epsilon naught. Now looking at the diagram, the charge enclosed is 2q and minus q. So it will be 2q upon epsilon naught and minus q upon epsilon naught. So 2q minus q, that is equals to q upon epsilon naught. We don't have to consider 3q because it is outside the Gaussian surface. Let's see the next one. Okay, the question over here says an infinite line charge produces a field. So electric field E over here is 9 into 10 to the power 4 Newton per Coulomb, that is our electric field, at a distance r, that is equals to 4 centimeters. So I'm just writing it as 4 into 10 to the power minus 2 meter. Calculate the linear charge density. Now we know that due to a line charge, electric field E is equals to lambda by 2 pi r epsilon naught, right? So we are looking for lambda from this question because r is given and E is given. So lambda over here will be equals to E into 2 pi r epsilon naught. Now majority of the students, they take the value of epsilon naught here and try to simplify. But better way is we can multiply up and down here with 2. Sir, why 2? Let's see. So it becomes E into 4 pi epsilon naught into r by 2. Now exactly. So 1 by 4 pi epsilon naught, that is nothing but 9 into 10 to the power 9. So if you cross multiply, we will get 4 pi epsilon naught is 1 upon 9 into 10 to the power 9. So electric field is 9 into 10 to the power 4, 1 by 4 pi epsilon naught. So let me put here 9 into 10 to the power 9. R over here is 4 into 10 to the power minus 2 whole divided by 2. So let's cancel 9 with 9 and 10 to the power 4 minus 2, 10 to the power 2, and 9 goes up. So 10 to the power minus 7 and 4 by 2 is 1 second, let me just write here 7 and 4 by 2 is 2. So that will be our lambda. And what's the unit? Coulomb per meter. So this is our answer for this problem. Yeah. Many of the student as a beginner, they take it as 8.854 into 10 to the power minus 12. Done? Understood? Yeah. Let's see the next one. So question over here says, a cylinder of large length means you can take it as linear charge, right, density, and a charge here is Q, that will be equals to 2 into 10 to the power minus, wait, charge of this Coulomb per meter. Now that's not Q, that's what, that's lambda, because look at the unit. So this is be very careful with the units are telling that this is not charge. Yes, many of the students reading this line, they think that this is our charge, but looking at the unit, it's lambda. Find the electric field at a distance r is equals to 0.2 meter, right? So we know that electric field E is equals to lambda over 2 pi r epsilon naught. Let's multiply up and down with 2, right? Yes, it becomes quite easier. So this becomes our 4 pi epsilon naught into r. Now we know that 1 by 4 pi epsilon naught, that is nothing but 9 into 10 to the power 9 2 into lambda, that's 2 into 10 to the power minus 8, and over r, which is equals to 0.2, right? Let's remove this point. We get here 10, and cancelling 2 with 2, it will be 18 into that becomes 9 and 1 10 minus, it will become 2. So the correct answer is 1800. So electric field is 1800 Newton per Coulomb. That's our electric field. Understood? Do the next one. So the question over here says a charge of this much Coulomb. So let me just write here Q, that is equals to 17.7 into 10 to the power minus 4 Coulomb, is distributed over uniformly over a large sheet. Now area of the sheet is here 200 meters square. Calculate the electric field intensity at a distance. Now R here is 20 centimeters. So 20 into 10 to the power minus 2 meter from it in air, right? So first of all, we know that due to a sheet, the sigma, okay, that is very important because the electric field here E is sigma upon epsilon naught, right? And sigma is nothing but Q by A, right? So Q by area into epsilon naught. Now Q here is nothing but 17.7 into 10 to the power minus 4. Area here is 200 meter square, right? And epsilon naught is 8.854 into 10 to the power minus 12. Now let's cancel out 17.7, that must be 2. 8.854 into 2, I think. Let me just multiply and check. So 8.854 into 2, that's approximately 17.7. So that will straight away cancel out, and here we get 2. So 2 cancels with this, we get 100. So 10 to the power minus 4 whole divided by 10 to the power minus 10, and 10 goes up 10 to the power 6 it will be. That will be our electric field Newton per Coulomb. Any doubt? Understood? We'll move to next one. Okay, so the question over here says a charged particle having a charge. So here Q is nothing but minus 2 into 10 to the power minus 6 Coulomb is placed close to a non-conducting plate having a surface charge density. So sigma over here is 4 into 10 to the power minus 6 Coulomb per meter square. Find the force of attraction. Now we know that force F is equals to Q into E. Now E is nothing but sigma by 2 epsilon naught, one side, because it's placed on one side, right? So sigma upon 2 epsilon naught. Now let's put the values. So Q here is minus 2, we'll ignore the negative sign. 2 into 10 to the power minus 6. Sigma is 4 into 10 to the power minus 6 whole divided by 2 epsilon naught, which is 2 into 8.854, 85 into 10 to the power minus 12. Let's simplify it. So 2 cancels with 2. We left with 4 upon 8.85 into 10 to the power. Now minus 6 and minus 6 minus 12, that cancels out. And when you divide this, you get 0.45 Newton. That's correct. We'll move to the next one. Here it is. So the question over here says a particle of mass 9 into 10 to the power minus 5 g. So let me just write here, mass is in grams. So let's convert it into kg. So 10 to the power minus 8 it will become. So minus 8 kgs is kept over a large horizontal sheet of charge density. So sigma is given here as 5 into 10 to the power minus 5 Coulomb per meter square. What charge? So they are asking Q, so that if it is released, it does not fall. So if something is falling, it is falling because of gravity. So simply force must be equal to mg. And force is nothing but Q into E, that is mg. And E for a sheet is sigma by 2 epsilon naught, that is equal to mg, correct? So here Q will be equals to mg into 2 epsilon naught over sigma. So let's substitute the values. M is nothing but Q will be equal to, M is nothing but 9 into 10 to the power minus 8. G is 9.8, acceleration due to gravity, 2 into 8.854 into 10 to the power minus 12. You can take it as 10, doesn't make any difference. Whole divided by sigma, which is 5 into 10 to the power minus 5. And if you simplify this, okay, I'll just directly write the value. It will be nearly 3.12 into 10 to the power minus 13 Coulomb. That's our correct answer. Yeah, fine it is. Okay, we'll move to next one.
says two large metal plates. So let's draw here two large metal plates, each of area 1 meter square. So this is 1 meter square and this is also 1 meter square. Are placed facing each other at a distance of 10 centimeter apart. So the separation is 10 centimeter and carry equal and opposite charges. So if this is positive, this will be negative. If the electric field between the plates is 100 Newton per Coulomb, so electric field E is 100 Newton per Coulomb. Find the charge on each plate. Okay, fine. So if it is positive, the field will be outward, and if it is negative, the field will be inward. So you can see that electric field due to the first plate will be E1 and E2, and both are pointing in the same direction. So net field will be E1 plus E2. And E1 is nothing but sigma by 2 epsilon naught, we learnt, plus sigma by 2 epsilon naught. So the total field will be sigma by epsilon naught, right? That is our electric field. Now sigma here will be a charge upon area. So we have to find charge, right? Yeah. So E will be equals to Q by area into epsilon naught. Let's cross multiply. So Q will be equals to epsilon naught A into E. Epsilon naught 8.854 into 10 to the power minus 12. Area is 1. So we can ignore this. E, electric field, is 100. So straight away it is 8.854 into 10 to the power minus 10 Coulomb. Any doubt? We'll move to next one. Okay. So here the first chapter overs. Okay. And